right. I think let's get started, everybody. Welcome to, I don't know if it's day 2 or day 3, depending on whether we consider the Tuesday night opening panel of the workshop on correlated extremes. Really excited to move into another densely packed day. I want to just spend a little time just sort of quickly reflecting on where we were yesterday and where we're headed for the next couple days. You know, I think it's fair to say after yesterday that we have a huge amount of content, especially on the climate science and sort of hazard description side of things. You know, we heard a lot from that perspective yesterday. Today, we're going to be transitioning a little more to sort of the bottom-up, impacts-driven, decision-driven approaches to thinking about correlated extremes. But you know, to put it candidly, to be blunt, as we look around the room, we have fewer people who can really sort of reflect that decision-maker context, who can speak to some of those bottom-up issues. So I think, you know, for all of us, as we're thinking about the breakouts that I'll describe, as we'll think about the report backs, let's all, those of us who really sort of live in that space, please kind of speak up, give us your perspective on what you heard yesterday, and let's all, you know, really sort of work to sort of wear that hat that sort of meets where the science and the decision-making and societal impacts are. Okay, so we all know what we did yesterday, but just to kind of walk us through where we're going, we are going to have this morning some more talks, and the first session that Amir's about to lead, sort of continuing in the veins of the sort of mostly top-down perspectives to correlated extremes. Then we're going to shift gears slightly and hear, I would say, a kind of detailed talks from 4 experts working on a particular type of extreme. And we'll hear about how, in analyzing that extreme event, they've already been kind of thinking about correlation, either sort of a multivariate space or other. So maybe you can think of that as kind of a bridge between traditional approaches to thinking about extremes, getting to correlated extremes. Then we have lunch, and then we're going to go into the breakouts that we've been talking about. More details on that later, but I wanted to go back to these sort of framing questions that I mentioned yesterday as a way of sort of encouraging us to reflect this morning. These are the kind of things that we're hoping to get out of these breakouts, which are going to be 15 people or so per breakout. And we've intentionally broken everyone up so people aren't able to kind of specialize in any one session. We want to try to capture the diverse set of questions in each of the breakouts. And before I turn things over, I just wanted to sort of quickly give some examples of a few reflections sort of spanning all of these topics that I either heard others make yesterday, you know, or have kind of been thinking about myself, just to give a flavor of some of the types of things that, you know, that we might talk about. So I think Kate's remarks, both during her keynote and sort of thereafter during the day, about how she looks to work with people who are interested in filling gaps. She sees that as a space where scientists and decision makers can meet, people who have a diversity of perspectives, people who are curious. And I think that's, you know, the spirit of what we want to try to do here. We heard from Kate about how decision makers are actually considering correlated extremes in some of their planning to date. We heard the night before about how even when there isn't a shared driver behind correlated extremes, they can be incredibly impactful. Think about Michael Oppenheimer's comments about how sometimes there's sort of a societal bank. And if you have too many extreme events in a given season, you can sort of blow through that budget and see catastrophic impacts of various types. Also struck by Adam Sobel's point about how, you know, even though correlated extreme events are sort of by nature correlated, in some perspective, it's sort of been the policy and impact communities maybe who have forced us or encouraged us to think about questions like how many severe hurricanes could we get in an individual year, you know, as one example that's particularly important for decision making. We heard yesterday a lot of talks about temperature, precipitation, surge, but we're reminded that we need to think about other variables as well. It's not just a dichotomy, for example, between hot and humid events, hot and dry events, what's happening to wind during those types of events as well, as one example of additional climate or sort of weather variables we need to be thinking about. We heard about absence of data being an issue. People want to incorporate ocean waves, for example, in more of what they're doing, but the data, limits what we can do in that capacity. We heard about the role of models in filling some of these data gaps. Thinking back to some of the talks early in the second compound event session, I think gave us some examples of what can be done sort of using models to fill data gaps in data sparse regions. We heard about limitations of different types of metrics. Are the traditional sort of blocking indices, omega blocks, appropriate for some of the types of issues we're looking at? As one example. We heard lively discussion about, as we sort of transition to impacts data, what's the role of observed, empirical, for example, epidemiologic data, as we're thinking about human health impacts of some of these correlated extremes, relative to process-based modeling approaches, which may be able to fill in some of the gaps as we think about how crops might be affected by sort of somewhat unprecedented conditions in the future. Maybe even we can have process-based modeling of how human health may be affected by some of these correlated extremes in the future. We heard that we lack data on what guidelines are actually being used in planning right now for much of the world. Another thing we need to learn. We need more socioeconomic data. We heard about not necessarily knowing what stakeholder thresholds are so important in different applications. As we're thinking about methodologies, we heard some arguments in favor of scenario-based approaches. The strengths of storyline approaches is something we can incorporate, even as we're also thinking about sort of cutting-edge statistical approaches. We heard about sort of trade-offs between precision and accuracy that I think will inform a lot of what we're thinking about as well. Certainly we heard about different timescales, from the weather timescale out to comments about the need to consider decadal variability in some of these correlated extremes that are emerging, especially in light of our short data records relative to the infrequent times maybe when we have multiple variables in these extreme states. So clearly we need to know more about the role of natural variability, and models can help us in that regard. We heard about the need to engage more deeply with statisticians, something certainly some people in the room already represent themselves and begun to do. But I think there's more to be done in that space as we think about organizations, meetings that we could engage more deeply with in this correlated extreme space. Statisticians, may be an obvious case of that. We heard a little bit about detection and attribution, in some ways brought up really in the context of climate communication, even advocacy through some of the remarks. So, just a flavor of some of the types of things that we heard about. We heard about the role of bureaucracy, sometimes being able to help move forward action. For example, in some of Michael Oppenheimer's remarks 2 days ago. So how do we kind of institutionalize some of this correlated extremes thinking so it's less subject to sort of the vagaries of politics, for example. And I think another theme behind all this is the need for funding mechanisms within the government as we think about resilience, role of sort of private sector, for example, to push some of this forward, but also funding for the core scientific work to build out some of this improved modeling and to build out some of this data. So definitely want to leave it there, but just sort of, and I should have mentioned, I hope folks were kind of looking over the questions and thinking about that. That's the kind of thing that we'd like to get out of the breakouts. That's the kind of thing we want to be reporting out on tomorrow. But feel free to go beyond these questions too. The key point is we really want everybody speaking in these breakouts. Our talks are very structured, and the agenda is very full of talks. But in a lot of senses, I think this is really sort of the most important aspect of the meeting from my perspective. So we're really looking forward to capturing everyone's perspectives over the coming 2 days in that regard. So with that, I'm going to turn things over to Amir, who's going to kick off our first session this morning.
Good morning, everyone, and welcome to the sequential and persistent extreme session. We have 6 exciting presentations coming up. Our first speaker, which is an invited speaker, is Olivia Martius from University of Bern, and she'll be talking about persistent surface extremes. Olivia.
Thank you very much. Good morning, everyone. I'm very excited to be here at this really stimulating conference and talk to all of you about recurrent Rossby waves and how they link to recurrent and persistent surface extremes. I will pick up the thread that Carly and Kai started yesterday, talking about Rossby waves, but proceed a bit further. But before I start my talk, I'd like to acknowledge the people who actually have done the work that I'm presenting here, my PhD students, Matthias Rötlisberger, Yannick Barton, and Mubashir Ali. And I would like to start with telling you 3 stories about recurrent Rossby waves and recurrent or persistent extremes. And I start with an example where we had temporal clustering of heavy precipitation that led to a very severe flood event. It was the largest flood event in southern Switzerland in the last 150 years in fall 1993. So what I'm showing you here today is catchment averaged daily precipitation in millimeters per day, indicated by the black bars, and the blue line indicates the 99th percentile of the precipitation. So what you can see is that in this time period between mid-September and mid-October, we had a series of 4 heavy precipitation events that exceeded the 99th percentile during this short time period. And now I would like you to focus on the gray shaded in the background, which indicates the lake level. And the red line indicates the flood level of the lake. And you can see that already the first precipitation event led to the flooding of the lake. But every subsequent precipitation event led to a further increase of the lake level because the lake level couldn't fully recover between these precipitation events, and the flooding just got more and more severe. So now we're interested in the atmospheric and the flow conditions that led to this temporal clustering of heavy precipitation. And I should say that each individual of these heavy precipitation events was associated with a distinct weather system. And they were all associated with very similar weather systems. Namely, they were associated with upper-level Rossby wave breaking, which is illustrated here schematically. On the right-hand side, you can see the Alps. And then, just to the west of the Alps, we have the breaking Rossby wave. And this breaking Rossby wave ensures the transport of moist air towards the Alps. So it's an atmospheric river-like flow situation. The structures are too short to actually count as atmospheric rivers that bring moisture to the Alps. The moist air is forced to rise and heavy precipitation sets in. But I would like to draw your attention now to the upstream wave signature that is indicated here, the synoptic scale Rossby waves, and I would really like to focus on these. And I would briefly like to introduce the synoptic scale propagating Rossby waves by showing you an example. What you can see here are 6 hourly snapshots of the meridional wind velocity and the dynamical tropopause. This is the black line. The dynamical tropopause is a proxy for the location of the jet stream and hence the waveguide. And you can see these waves as sequences of positive and negative meridional wind velocity signatures, and they propagate along the waveguide towards the east. If we want to visualize this propagation in a very succinct manner, we can use so-called Hofmöller diagrams. And for these Hofmöller diagrams, we average the meridional wind velocity meridionally and plot this information in a framework where we display longitude versus time. And this then provides us with a depiction of the propagation of these wave trains. We can also, from these Hofmöller diagrams, infer information about the group velocity. The group velocity is the propagation speed of the entire wave packet and the phase speed of these waves. So the phase speed is the propagation speed of the individual troughs and ridges. So now I'm going to show you a Hofmöller diagram for the flood event in 1993. So you have longitude on the x-axis, time along the y-axis, and the colors indicate the meridional wind. The black crosses mark the location and the timing of the heavy precipitation events. And I will now like to ask you to focus on the wave signatures upstream of these heavy precipitation events. So to focus on in this area here, where you can see that the waves are very well organized. There is a regular pattern in where the wave troughs and where the wave ridges are located across a sequence of individual wave trains. So we have a phase locking, a quasi-phase locking between a series of Rossby wave trains. And the wave trains are illustrated here by the red lines. They indicate the individual wave trains, and then I have also highlighted the phase speed, so you can see that these are propagating waves, and they're all in phase with each other. And this kind of pattern we call recurrent Rossby wave patterns. So these are a sequence of Rossby wave packets that form a recurrent Rossby wave pattern, and such a recurrent Rossby wave pattern played a crucial role in the temporal clustering of these extremes on the Alpine south side. Now, I'd like to move on to a second story, now focusing on temperature extremes, and I'd like to introduce you to an example of a cold spell that occurred in Europe in February and March of 1987. And you can see again the Hofmöller diagram, and again I highlighted the Rossby wave trains, and you can see that they're again organized in a very persistent phase locking. And this leads, basically phase, being in phase of the subsequent Rossby wave trains, leads to a sequence of northerly flow episodes over Europe and to cold air advection, and this results in a cold anomaly over Europe. So you can see here the normalized temperature anomalies during that time period. If the waves are in a different phase, so if we have southerly flow over Europe, that can result in heat waves, and I am showing you one example here where you can see again such a recurrent Rossby wave pattern upstream over the Atlantic, a series of Rossby wave trains, and then over Europe where we have a sequence of southerly flow episodes, a persistent heat wave. And since these wave trains cover more than just one wavelength, what you can see here is actually that at the same time we also have a heat wave over Japan, also associated with southerly flow episodes, associated with the same wave trains that led to the warm air advection over Europe. So I've now introduced several case studies, and you may wonder, well, how relevant are these recurrent Rossby waves over a climatological time period? And to address this question, we have derived an objective measure to extract the magnitude of recurrent Rossby waves, and I don't have the time to introduce this measure here. You can look it up in the paper by Matthias Rötlisberger that just came out in Journal of Climate. So we take these time series of the recurrent Rossby wave measure and combine it with time series that provide information about the duration of hot and cold spells extracted from ERA interim. Then we feed both of these time series into a Weibull regression model, and out of this regression model we get a so-called acceleration factor, and this acceleration factor describes the increase in the percentiles of the hot or cold spell duration distributions per unit increase in this recurrent Rossby wave pattern measure. And we can then plot a map of these acceleration factors. And this is shown here. So this is for the extended summer season in the northern hemisphere, the result of the Weibull regression, and shown here is the acceleration, or the acceleration factors. Red and orange colors indicate significant increase of the hot spell duration given a recurrent Rossby wave pattern was present upstream of a specific grid point. So what we find is that there is indeed a statistically significant link between these recurrent Rossby wave patterns and the duration of hot spells. I'm not showing the cold spells here. And what we also see is that we get a wave-like pattern again in these in these acceleration factors. It's a wave number 7 pattern with positive contribution of the recurrent Rossby waves to the hot spell durations over Europe, over the Western US, Western North America, and Russia and Central Asia. So, to conclude, recurrent Rossby waves arise from a sequence of synoptic scale Rossby wave packets that each amplify in the same geographical region and in the same phase. I've introduced several case studies and showed how these recurrent Rossby waves may lead to recurrent precipitation extremes. I have also illustrated how they are related to persistent surface temperature anomalies. And we have illustrated that this link between recurrent Rossby waves and surface temperature anomalies holds also for climatological, over climatological time periods. So we suggest that besides blocking recurrent Rossby waves should be considered as a further mechanism for generating unusually persistent surface weather. What we're currently doing is looking at the causes of recurrent Rossby waves, their potential role in predictability of such episodes, and of course long-term changes. So thank you very much for your attention. And I just would like to highlight, because I saw other people advertising open positions as well, there will be an open position for a postdoc focusing on temporal clustering of tropical cyclones. If you're interested, please get in contact. Thank you very much for your attention.
For your presentation. We have time for 1 or 2 quick questions.
Oh yeah, thanks, Olivia. This is great, great talk. Can you show me the previous slide quickly? So I think this is very, this overlaps very much in pattern with the stuff that Kai showed, right? So wave 7 type pattern. My question is, are these kind of individual events, or is this also in your analysis based on co-occurrence in these regions? Thank you.
Can you hear me? Yes, so I showed you one example where there actually was co-occurrence, but it's not a requirement. So we don't require these recurrent Rossby wave patterns to extend all along the northern hemisphere. And I would argue that, well, not all of them are linked to extremes happening in several locations around the world, but they can be.
Did you look at whether these medium timescale waves are associated with a more long-term basic flow that underlies them? Why do we get these things?
Yes, that's exactly the kind of questions that we're looking at the moment. So that's exactly what we're interested in. The question, is it the background flow that's most relevant, or is it or is it the triggers of the waves? So is it maybe a very active MJO, or is it a blocking episode that triggers these waves? And my hypothesis is it's a combination of the two, but the background flow will likely play an important role.
So let's move on to the next speaker. We'll have more time for questions later. Our next speaker is Meredith Fish from University of California, San Diego, and she'll be talking about atmospheric rivers.
Okay, how's this? Before getting started, I'd like to thank my co-authors and collaborators, Anna Wilson, and my advisors, Art Miller and Marty Ralph. So the term atmospheric rivers has been, hold on, sorry. The term atmospheric rivers has been thrown around a bit in the past few days, so let's start by providing a more formal definition, which that is a long, narrow, and transient corridor of strong water vapor transport that is typically associated in the cold in the cold front of an extratropical cyclone, and the water vapor is typically supplied by tropical and or extratropical moisture sources. These events are typically identified by their length and width ratio. What you typically see, or what one would expect, is shown in the bottom, a figure in the bottom center, which is their IWV, or your integrated water vapor transport, which we usually get from satellite measurements. ARs are also identified by the combination of both moisture and wind, which is calculated via IVT, or your integrated vapor transport. And this combination already is pretty much a correlated extreme. So what kind of made us want to look at ARs with a connected extreme session? And where we really came from is during water year 2017, the public meteorologists and our own group were really noticing the frequency of these back-to-back atmospheric rivers. An example of these successive events is up on the left, depicting the IWV and the geopotential heights at 850 hectopascals from February 3rd to 10th, 2017. During this time, 4 ARs made landfall in Northern California, and they were embedded with mesoscale features. Also during this time was the Oroville Dam crisis, which had damage to the main and emergency spillways, which prompted the evacuation of over 180,000 people. So all of this kind of led to the questions of how often do ARs occur in close proximity to one another, and really how different was water year 2017 compared to the rest of atmospheric river families. So before we can officially define what successive atmospheric river events are, we need to define an AR event itself. And there's plenty of really good research being done in this area to identify these events. But what we were really looking at in this case was Atmospheric River Observatory hourly data that's taken up in Northern California, about an hour and a half north of San Francisco. These are point and observational data sets, and not using a catalog of AR objects, we then looked at AR conditions using 3 criteria: 8 hours of consistent integrated water vapor greater than 20 millimeters, and a bulk upslope moisture flux of 15 centimeters per meter per second, or the amount of moisture that is fluxed directly perpendicular into mountains. We then identified and counted AR events which occurred within various aggregation periods. In this, we identified them as the lengths of time between the end of the first AR and through which successive ARs would occur, and we would count them as AR families. Those which occurred outside of this aggregation period were then termed single AR events. We also wanted to calculate and look at 2 different subsets of AR families, which we thought would have different dynamical reasons and features, as well as different impacts. So we looked at AR events which occurred within 12 hours of one another, which we termed dual AR event AR families, and those which had 3 or more AR events, which we in 120 hours, which we termed multi-AR event AR families. So as what we've been talking about over the past few days, one of the first things that we really needed to look at was really what even was the aggregation period that made sense for successive temporal clustering. So instead of just picking one, we looked at everything actually from 12 to 600-hour aggregation periods, as is shown on the bottom figure on the left. The figure shows the number of new AR families on the y-axis and the aggregation period on the x-axis. And you can see that there's multiple places where AR families initiate and then they plateau. So one of the first places that the additional AR families plateau is around 120 hours. And this is concurrent with what we find in cyclone family literature, actually, where clustering happens in that 6 to 9 day time period. The reverse plot is also shown in the bar chart on the left, which shows the new number of AR families per period. So what we also wanted to look at was not just how the number of AR events per family changed as the aggregation period extended. And instead of more AR additional families being considered, you instead have longer, more AR events per AR family, as is depicted by the average in the top of the bar charts, where the number of AR families that have 2 to 6 events actually increases. We also wanted to explore the seasonal and interannual variability of AR families and how it related to AR events in general. And we found that similar to AR activity, the majority of AR families occurred also in the winter months of December, January, and February, with roughly equal frequencies in the shoulder seasons of spring and fall. We also noted the large interannual variability of AR families, which some dependent on both the water year but also on the length of the aggregation period. Extending this analysis past the plot up here of 2017 into 2018 and 2019, we see that 2017 was still the peak, but that 2019 was not far behind, as those in California would know that we had many instances of rain this past year as well. So now that we've identified these AR families, the next thing that we needed to look at was what were the common synoptic features of them. So the plot up here shows the anomaly from the different various synoptic patterns compared to a DJF climatology calculated over a 30-year mean. And we note, so the anomaly is shaded in the DGF climatology as in line contours. And we note that AR families typically have lower geopotential heights off the coast of British Columbia at both 850 and 500 hectopascals. And that's similar to AR activity in general for this area, so that's not really surprising. We also note that there's enhanced wind speeds at 250 hectopascals off the coast of the US West Coast, which is important for identifying regions of development or suppression. And we also found that higher IWV values that corresponded to AR families, which is consistent with results from Payne and Magnuster on persistent AR conditions in the region. We also wanted to compare AR families not only to a climatology, but also within themselves, and in this case in particular to single AR events. Shown up here is an example of an AR family propagating up across the Pacific in the top versus a single AR event making landfall in the bottom figure. And what we're able to see is that actually there are significant differences between these two data sets, two subsets. And what we're seeing is that there's significant regions of zonally extended low areas of geopotential heights in both 500 and 850 hectopascals. We also have a stronger and more northerly subtropical high, which would further limit the southward propagation of secondary AR events, keeping them constrained to Northern California, which is where this data is located anyways. AR families also exhibit faster and more zonal 250 hectopascal wind speeds, and we have higher moisture content closer to coastal California. So we've also been talking about the impacts of these successive or clustered events, and we also thought about this when trying to identify subsets of these groups. So as one would consider, from a hydrometeorological perspective, the longer lasting an AR family, the greater the potential for saturated soils and higher stream flow. Therefore, given the right preconditioning provided by the first events in a family, there's a potential increased risk of hazardous impacts. So these two are forecast plume diagrams of two forecast examples of both the dual AR event AR family and a multi-AR event AR family, which, to remind you, is the 2 events in 12 hours versus more than 3 events within 5 days. And anywhere that is above the black line of 250 IVT units would be an AR conditions are predicted. So between these two subsets, we actually see that there are significant differences between these two different types of AR families. In particular, I'll note the lower geopotential height region for multi-AR event families that extends into the tropics at 850 hectopascals. We have a maximum wind speeds at 250 that's shifted further south, closer to the tropics and a little bit further west off the coast of California, as well as more different moisture regions starting to emerge where multi-AR event families are a bit more connected to the tropics, where these single AR event families are more consistent and constrained to the mid-latitudes. The higher moisture and warmer temperatures around Hawaii are also suggestive of this subset being more like the Pineapple Express type storms that were first identified as an AR event in our literature. So going back to our motivation, we really wanted to quantify how odd water year 2017 was in comparison to all other AR families. So during this time, there was 34 ARs that impacted Northern California, and according to this analysis, that means that we had 23 AR families. It was also the wettest year on record for the 8-station index in the Northern Sierras, surpassing the 1982-83 record by mid-March. The composite difference on the upper left now shows water year 2017 differed from all other AR families in a variety of ways. First, we see this strikingly two significant and persistent high geopotential height regions that helped funnel storms into Northern California. And with the extended region, you would look and actually see a Rossby wave train-like pattern that we've heard about yesterday and over these past few days. We also looked at the large magnitude of water vapor. Oh, there it is. That was off of and south of California that we think made the largest impacts for this water year in Northern California. So while I don't have too much time, as I'm already running close to the end to go into detail on this work, we're also starting to assess the predictability of these and the relation to other large-scale extratropical and tropical drivers. So we're trying to evaluate both the stationary and transient components of AR families and really how they relate to these other large-scale phenomenon. So we're looking at the relation to cyclone families and as well looking at waveguides, wave breaking, and jet dynamics. But this really all started from kind of realizing that we needed to connect it to something else during the ENSO of 2015-16, where we all expected really large storm activity in Southern California. And while we had rain, it wasn't the canonical El Nino that we were expecting. And this perspective changed after winter 2016-17, when there was the short-lasting weak La Nina conditions that ultimately switched to neutral by December, midwinter time, and Northern California was consistently slammed with storms. So this shows that we really need to take into account and consider other large-scale atmospheric drivers besides the standard that we use in California, such as ENSO, to help us really assess the predictability of these successive storms. As we've been talking about today, they are so important for us, especially for water resource managers. So with that, I will keep up some conclusions and finish up. So AR families, we're saying, are a very distinct class of extreme weather events and are important to understand as they often increase flood risk, they threaten property, and they disrupt lives. Half of our events within our catalog from 2004 to 2017 occurred in AR families. That's over 100 AR events during that time period. We also say that AR families occur with preferential atmospheric conditions. They're distinguishable from single AR events, and there's significant differences between two different subsets within the group. As always, there's plenty of future work for me to finish out my PhD on this project, but with that, I'll take questions. Thank you.
Thanks, Meredith. Maybe one or two quick questions, Bradley.
Great talk, thank you. Curious whether you've looked at the sort of snowpack components to it. Is there a tendency for one of the sort of sequences to run a little warmer, lead to snowfall, elevations moving, to sort of how that, I guess, sort of temperature advection piece into the mountains could relate to rain on snow, flooding aspects?
Yeah, I specifically haven't looked into that, but I know other people in my group are really interested in the changes of snow level. It is something that I should be taking into account with this work. Particularly the area that I work on is a more coastal mountain and not inland. So as we extend our research areas into other watersheds that actually are driven by snowpack, I think it'll be taken into account a bit more.
Any other questions? Yes?
Thanks. That was a really interesting talk. I was just wondering, what are some of the other drivers that you think could be important? You mentioned towards the end that we should consider things other than ENSO.
Yeah. One of the things that we're really finding is jet dynamics and just the presence of jet extraction versus retraction, as well as definitely Raspberry wave trains and waveguides. Those seem to be the strongest ones, but there also seems to be a little bit of a connection to MJO and to SSTs in the tropical Pacific.
Great. Thanks, Meredith. Let's move on to the next speaker, Colin Zarzicki from Penn State, and he'll be talking about winter storms.
All right. Had a great time the last couple days. Looking forward to another good couple days. I first want to acknowledge my co-author on this presentation, Alan Rhodes from Berkeley Lab. He's been actually doing a lot of the work with me in terms of kind of the sequential event analysis that I will talk about in the latter stages of this talk. So northeastern United States winter storms. So the northeastern United States is kind of a regional focus, but essentially where we are right now, tends to kind of have these synoptic scale extratropical cyclones that move through the area in the winter and the early springtime. And by nature, these are essentially compound events. They can have very significant precipitation impacts with many different phases: rain, snow, freezing rain, but also wind and storm surge. And because of this, these are kind of one of the primary weather phenomenon in this particular region of the United States that have significant societal harms. So the goal for kind of what we've been working on the last few years is to essentially be able to define what we consider storm level metrics. And when I say a storm level metric, the idea is to actually be able to go in and data mine weather and climate data using a direct, objective, dynamical quantification of these events. So to not have to use some sort of downscaling product to actually kind of pull these storm level statistics out of some of the climate data products that we've already actually heard about the last couple of days. So it's really kind of a two-step process. So The first step, and I don't want to get into the nitty-gritty specifics of this, but essentially what we have to first do is actually find the storms themselves within the data sets. So we use kind of a simple Lagrangian tracking framework, and what we do is we just kind of track sea level pressure minima regionally in the eastern United States. And we have a suite of criteria, such as kind of how strong the sea level pressure minimum has to be, where the trajectory is in such a way that we can constrain the regional impacts, and kind of a persistence that the storm has to exist for 24 hours. But this kind of allows us to build a large compendium of kind of these storm-like events that impact this particular region. Then what we can go on and do is when we've defined all of these particular storms, we can apply some sort of societal or impact-based metric. So for this talk, I'm going to focus on kind of using an integrated precipitation quantity. So we have kind of based this off of the regional snowfall index, which is a parameter that's been used here at NOAA to kind of classify snowstorms. But we've also modified it. We refer to it colloquially as the regional precipitation index to kind of also include a broad range of hydrologically impactful storms. And the idea just really simply is to take kind of the integrated precipitation associated with one of these storms, such as you would see in the bottom left, and you kind of marry it to population density, such that you're really kind of tying in where the precipitation falls to where individuals are. And you can kind of use this metric to, categorize these storms. And again, I would refer you to this Squires et al. Paper for the specifics, but the idea is to kind of, somewhat analogous to the Saffir-Simpson scale or the Fujita scale for tornadoes, to kind of have this hierarchy of impacts-based events ranging from Category 1, kind of what we would consider more of a low-end nuisance-type storm, to a Category 5, more extreme kind of systems, with increasing return periods. So obviously, the more intense storms we see much less frequently in the observed record. So just kind of one example of how this kind of objective technique, this kind of data mining works. This was a particular storm that we had a few years ago. It was #Snowzilla on Twitter. But on the left is kind of what we can define objectively using a reanalysis product, in this case JRA55. And on the right, this is a hand-curated data set produced by a forecaster or climate data analyst at NOAA. And what you can see is without the need for manual intervention, we can kind of recreate these features. So we can have confidence that we move to things like climate data sets where we do not have an observational record and we do not have a grad student kind of going through and checking off yes storm, no storm. That we can actually get robust climate statistics on these phenomenon. And I do want to emphasize that we're also very kind of cognizant of the community nature of how this kind of extreme weather classification works. So we really strive to kind of make these tools open for other folks. So I just want to highlight that a couple of these packages that we use.
Okay, folks. We're going to reconvene. Obviously, we're very sorry this happened. Major wrench. I'm sure there's a joke about a correlated extreme event we could make here, but we won't. We are about an hour and 45 minutes behind the sort of published calendar associated with the event on the website. Here's what we're proposing to do. We're going to keep going through the agenda where we left off, beginning with Colin, who's mid-talk, of course. We are unfortunately going to have to eliminate the discussion time within each session. We're just going to keep going with talks. At 12:30, wherever we are, we're not going to be through the material that's slated to end at 11:50. We're not going to be all the way caught up. But wherever we are at 12:30, we are going to stop for a 35-minute break, lunch, for those of you who weren't able to get lunch yet. Then we're going to reconvene at 1:05 or so, wherever we are in the morning agenda, as listed online. We'll get through the remainder of those talks, and then we'll go into an abbreviated afternoon session of breakout discussion. Do the full session on sectoral perspectives of societal impacts, which is slated to start at 2:30. It might start a little later, but we'll do that session in full, also with no discussion at the end of it. And then we're going to try our absolute best not to shorten the poster session at all, which is slated for 4:35. It may start a little late. If it does, we're exploring being able to have it go past a little past 5:45 for those who are able to stay a little longer. So bottom line, We can have it till 6:15. So we're going to pick up the agenda where we left off, but we will be stopping at 12:30 for a 30-minute lunch, wherever we are in the agenda at that time. And then at 1 or 1:05, we will pick up to finish off the quote-unquote morning agenda as listed on the website. After that, we'll go into an abbreviated breakout. Okay, so apologies. Thanks, everyone, for rolling with this. And special thanks to Colin for enduring this and being resilient. So come on up. Okay.
Well, thanks, guys. I mean, I've heard of students pulling the fire alarm to get out of class, but a gas leak is, that's really next level stuff.
This is the longest talk ever.
Sorry, I didn't time it, but we didn't have 2-hour windows. No, so I think where we left off was I was just kind of highlighting that. One of the things we really try to endeavor is to kind of make these tools available and make them, open source. So, if anyone's kind of interested in this type of storm level, framework for kind of some of these more phenomenological features within the climate system, please talk to me or check out some of our GitHub accounts. So the application I'm going to talk about in the last few slides in this talk, so we're using a large ensemble of climate simulations. So some might be familiar with this. This is the Community Earth System Model Large Ensemble. So it's actually 35 members of perturbed initial conditions using NCAR's climate model, and we run it from 1920 out to 2100. The three periods that I'm focusing on are periods that have high temporal frequency output. So 6 hourly output is needed for kind of the tracking that I discussed before the break. And so the idea here, really, the emphasis I want to make is that we have 1,260 total years. So really the goal here is to be able to have kind of robust statistics of kind of these storm level events such that we can assess kind of things like their sequentiality. So this is kind of an example of what gets spit out of this data mining technique. These are kind of what tracked storms look like that impact the northeastern United States. And again, with the emphasis that, we can track these cyclones globally wherever we want, but we're really trying to focus here on the northeastern United States. And you can see that we can kind of track the entire life cycle of these storms. So where they form, we kind of have these distinct areas of some storms kind of forming out here. Well, that's not showing up, but over the central United States and in the Gulf. But in general, you kind of see this trajectory as they deepen and kind of strengthen along the Gulf Stream and along the coast, and then they move up. So, one thing we can obviously look at with kind of the storm level approach is just kind of the mean climatology. So, one thing that we see is this is plotting the storms that we track for the snowstorms as a function of category. And again, reminding you that category 5 being kind of the least frequent but most intense events, category 1 being the most frequent but, kind of more nuisance level. And what we see is generally that as we move through the coming century, we see a broad decrease in snowstorms. But what's important to note is that, when we bootstrap on the top, this is looking at all snowstorms. We have very high confidence that we see a decrease in these discrete storm level events by the end of the century. But almost all of this decrease is a function of kind of the weak tail. So this is kind of the weak storms are really driving this decrease. And if we look at these really intense events, the category 3, 4, and 5, while they are less frequent, we actually see a much less clear signal kind of in how these storms are going to change in the future, with some members predicting more of these storms and some predicting less. So I just want to show a couple quick slides on kind of how we can use this analysis to really get at the climatological changes. So this is just kind of isolating the precipitation and just kind of the storm, or so we remove the precipitation, just isolate the thermodynamic impact. What we see is that the season that can thermally support snowfall using a precipitation typing algorithm decreases significantly as we move to the coming century. That's what the difference plot on the bottom is essentially showing, that the number of days that we have within our winter period that can support snowfall decreases. That is extremely consistent with some of the climate talks that we've already seen. So really the question is, why do we kind of have this nonlinear response in the tail of the distribution? And to kind of keep things moving along, I'm not going to belabor this slide too much, but essentially what we see is I want you guys to focus kind of on the bottom 3 panels. So this is the increase in the frequency of extratropical cyclones along the eastern seaboard that could theoretically, when the synoptic conditions align, produce these kind of tail snowfall events. So, what the last two slides are really telling us is that we have kind of this competing impact, and it's nonlinear across kind of the intensity spectrum, where we have a warmer atmosphere so that we have less kind of capability to produce snowfall. But when these storms kind of move up, since they're carrying more precipitation with them, when we kind of get the thermal conditions to align for snowfall, that we have a proclivity kind of for these more intense events. The reason why I kind of want to move through that a little quickly is I kind of want to really spend at least a couple minutes on these last couple of slides, which is really now starting to get into the sequentiality and really kind of what ties this analysis into the workshop. And I emphasize this is fairly new work, so if anyone has any suggestions or feedback, please come up and talk to me afterwards. But the idea is we can actually look at kind of the return values for these type of systems, so how frequently these storms kind of follow one another in the data set. So on the left, this is kind of how many of these sequential storms you get per decade as a function of how long it occurs between the storms. On the left is snowstorms. On the right is what we would consider high-end precipitation events, and these are the vast majority of these we would consider heavy rainstorms, heavy winter rain systems. And what you see is very consistent with what I showed on the previous couple slides, is that you see this kind of significant shift in the partitioning between how the Northeast is going to experience rain and snow in a sequential nature with these events. So you're kind of moving towards less successive snowfall in the future, but more successive rainfall, which has an impact on hydrology, and that's kind of what I'll just finish up talking about. So we have a project that has a lot of stakeholder engagement. Chesapeake Bay, Susquehanna River Basin, so kind of some of the more hydrologically based folks around the northeastern United States have consistently told us that from their kind of operational perspective, they're very interested in high runoff and rain on snow events during kind of the winter and spring seasons. So for example, a rain on snow event could be caused by having multiple successive snowstorms, which are then followed by maybe a period of warming and then a rainstorm, where you kind of get this compounding effect of snowmelt, runoff, and precipitation. So this is kind of an example of what we're starting to look at. This is the combination of, in red, this is the change, the daily change in surface snowpack. In blue, this is kind of the daily precipitation, and in green, which is a little hard to see on these slides, the daily runoff. What I want to emphasize here is this is a particular time series of a historical period, 1996, 1997. 1996, the Northeastern United States experienced their most significant flooding event that was not tropical cyclone related. It was due to one of these rain on snow events where you had a large antecedent snowpack from multiple snowstorms followed by a rainstorm. And what I think is kind of interesting is these are three different observational products, LIVNA, NLDAS, and JRA, and all three of them have a very significant representation kind of one of these kind of events. So when we're thinking about these things sequentially in the historical record, I think we need to be very careful in terms of our observed data set. And then the last slide is just kind of where we're trying to take this with regard to climate data. So this is, again, using the large ensemble. I'm just plotting one member here. But what we can do is we can kind of flag these very flashy high stream flow. We can kind of proxy them by a rainfall, a snowpack loss, and a surface runoff kind of criteria. And what we can do is we can find that the vast majority of these events can actually be tied back to a particular storm and a particular storm sequencing. And that's kind of what we're showing down here on the bottom left, is that, so in the bottom left, this is extratropical cyclone events. The x-axis is the change in snow water equivalent. The y-axis is kind of the amount of precipitation you have, and the size of the bubble is how much runoff you have. So what we can do is we can kind of use these multivariate proxies to kind of evaluate the hydrological impact that are coming out of these, in some cases, fairly low resolution 1-degree climate models, which can then be passed back to hydrologists and other impacts-based researchers for kind of more of these downstream metrics. And then, really kind of the preliminary take-home from what we've seen so far is over here on the right. And this is just, again, kind of mean statistics looking at the big picture sequencing. But in terms of events per decade, what we see is as we progress through the end of the century, we see a reduction in kind of these rain on snow events. So we see a reduction in kind of snowfall that is followed by rainfall associated with extratropical cyclones of about 2.9 events every decade. So from a kind of a present day value of 5.7 per decade. And then currently we have these kind of more flashy, what we call high runoff events. Maybe we have 17.8 per decade, so maybe 1, 2 a year. and we see a significant increase in kind of rain followed by rain events moving forward, where you're preconditioning the soil, saturated soils, and then you get more of these cyclones that kind of come through and give you these high runoff and high stream flow events. So, what this is really telling us in summary, I just want to note that we're developing these objective tools to kind of go through and data mine, weather and climate data sets to really kind of get the storm level events out so we can look at more of these sequential and persistent events. But I think what we're beginning to see, and this is kind of, I think what really ties into the theme of the workshop here, is that we're really seeing a fundamental change, or we're projecting a fundamental change in the sequential nature of these events. So we're moving away from more consistent snowpack and more consistent snowfall to kind of more of these very ephemeral snow events and these really kind of high runoff sequential rain type storms. And this is something we really want to, like I said, push forward with the hydrological community, impact space community moving forward. So thank you for making it back and your time.
Thanks, Colin, for the presentation, and sorry we don't have time for Q&A in the rest of this session. Small change in the order of presentation. Our next speaker is Arlene Fiore from Columbia University. She will talk about pollution and heat waves. Yes, or this one. Either way.
Good morning, everyone. I guess the benefit of the fire drill is I went and got coffee, so I'll probably talk even faster than I would have already. I'm being a little sarcastic here. But I'm really excited to have the opportunity to share with you, and thanks to Colin and Radley for this opportunity, some work that we've been doing and thinking about how can we start to mine some of these large ensemble, or at least small ensemble of chemistry, climate model simulations that are available to extract ideally useful information about air pollution events. And here we're going to try to look at temperature or heat and two different air pollutants, ozone and particulate matter, together. I should acknowledge my collaborators, and in the acknowledgments, this is a small piece of a larger project that we've been working on, and I'll come back to that at the very end. So this image is from the summer of 2012. There was a heat wave that affected much of the eastern U.S., and these are ozone fields that we're looking at. And actually from the talk this morning, I started wondering whether this is a recurrent Rossby wave pattern or blocking or both, and it would be interesting for us to connect with some of the dynamicists and figure that out. But we're not going to get into that kind of process level in this talk. So here now I'm combining the top panels, what you just saw. The middle panel is the PM. And just to show you that the particulate matter, these two different pollutants are kind of moving together. And this talk will focus on summertime, which are really our photochemical pollution events, which is not to discount the importance of understanding our cold weather events as well that affect, for instance, India and China. But the bottom panel here is showing the weather patterns, and Michael Wehner's talk yesterday really resonated with this point about it's not always the extremes of all of the variables that contribute to the events we care about. And it's been well established in the 80s and 90s that the highest ozone episodes are typically in the eastern U.S. associated with kind of weak high pressure systems that slowly migrate across the region. And then when the cold fronts come through, things clear out. So the question that we're after is, we know from the climate community that we expect, all else equal, right, more heat waves as mean global temperatures warm, at least based on thresholds that we define relative today. And so the question is, does that automatically mean that our air quality is going to deteriorate? Okay, so our approach here is an empirical orthogonal function analysis that we're really using as a data reduction tool. And so our goal here is to identify regions over the eastern U.S. that vary coherently, where the pollution goes up and down together. And this reduces the size of our data set for analysis, so that instead of having a time series we're looking at in every single grid cell, we instead have one time series per broader region. And then we can analyze kind of those time series. And again, ideally, the goal is to come up with information that may be useful for air quality or possibly even climate management. So as a proof of concept, before we jump to models, we wanted to apply this approach to a data set where we know what the answer is and confirm that we can get out the changes in frequency of pollution events that we know has happened in the eastern US over the last decade or so due to emission controls. And in the case of ozone, those emission controls are on precursor nitrogen oxide emissions. In the case of particulate matter, it's largely sulfur dioxide as the major precursor for summertime photochemical particulate matter. Okay, so this is an example for the northeastern US. The EOF is basically one of our patterns of underlying spatiotemporal variability in the system. In this case, we're working with a data set that's similar to what Jana Silman showed yesterday over Europe. These are Jordan Schnell's approach to providing girded observational data sets. We have ozone, PM2.5, and daily max temperature. So this is the Northeast US pattern, the associated time series, which for all of this analysis, we've oriented our principal components so that positive means an increase in the variable being shown. And if we draw a line at 2007 and we arbitrarily count the number, or we arbitrarily draw the horizontal upper dashed line and count the number of times that this time series exceeds that value and call those our high PM2.5 days, we find a sharp decrease from over 100 events before 2007 to only 18 in 2007 and beyond. And this is what we know has happened based on plenty of work in the literature and as we'd expect based on the reduction in precursor emissions over this period. In the interest of time, I'm going to flash this next slide. We did the same thing for ozone. We get the same answer. Just to show you that we're not just focused on the Northeast, we have these 5 patterns that together explain over 75% of the spatiotemporal variability in our data set. So all of this analysis, I'm going to focus on the Northeast. I'll show you a summary slide for the broader regions coming up. So this is so far on the observations. We do, for whether PM or ozone, we get the same patterns. So I'm going to jump next to what we're doing in the model. So we have a very small ensemble of 3 members that we've run with the GFDL chemistry climate model in which we follow the RCP 8.5 scenario, but only for the well-mixed greenhouse gases. So we're holding our air pollutant precursors at 2005 levels. And then we allow climate to change. This is a full chemistry climate model, so the chemistry is interacting with the climate system. And what we find is that by mid-century, if we focus on the northeastern US, we have about a 2 degree increase, over 2 degrees increase in temperature. And by the end of century, it's over 4 degrees increase in temperature. And so just to show you that we've looked at these patterns, if we run the same empirical orthogonal function analysis on the different ensemble members from the climate model, and we get roughly the same pattern. So we're not seeing major changes in these patterns due to climate change. What we're going to focus on is the frequency at which these patterns are expressed through these principal components. So this is a messy example of what one of these principal components looks like from 2006 to 2100 for the Northeast pattern. And what these lines are the upper quartile and lower quartile. And so if I kind of shade in this upper quartile, maybe you can see if you squint, it looks like there's a bit more density in the end of the later years of the 21st century. Importantly here, we're defining these quartiles based on the entire time series, okay, from 2005 through 2006 through 2100. So what we did next is a counting exercise and just simply say, how many times does in a given summer, does this value go above that upper quartile threshold? We do this for each ensemble member, for all of our regions, et cetera. I'm focusing again on the Northeast here. And so the different colors here are that counting exercise for each year for each of the 3 ensemble members. And so I would actually argue this looks to my eye, it's noisy first of all, a little more of a step change, but if we just do a simple linear fit for illustrative purposes, we would conclude that we get anywhere from 16 to 20 additional summer days that are in this upper quartile at the end of the century as compared to the beginning of the century. So we did this for all of the regions, all of the variables that we're looking at, and so this is a summary here of basically, if I go back for a second, this slope for the same kind of plot here, averaged over all three ensemble members, are the values that I'm reporting here. And so we see that for some regions, there are increases in PM 2.5 and or ozone and temperature. Not surprisingly, temperature is increasing dramatically, right, with the majority of summer days now above that upper quartile threshold that we chose. In the southern part of the country, however, we don't see these increases in PM and ozone along with temperature, and this is perhaps consistent with earlier work that suggests that that region of the country, pollution doesn't really correlate that strongly with temperature, and it's better correlated with humidity. And I wanted to note Charlie White's poster from yesterday, where he's kind of getting more into some of the meteorological drivers for these kinds of events and relationships. Okay, so the other question we wanted to look at was not only the frequency of these events, but how is the duration changing? And I'm looking at Jeremy Hess, who may be able to say whether it matters from a human health perspective as to whether there's sort of an increase, whether you're exposed to high pollution multiple days in a row versus if you have sporadic days where the bodies are covering. I don't know, but it seems like that might be something of interest. So what we're doing here is asking the question, once we go into that upper quartile on a given day in a given summer, how long do we stay up there? And we've classified these events somewhat arbitrarily into 1 to 2 days, 3 to 4 days, and 5+ days. And so not surprisingly for temperature, we've moved from short duration events to long duration events just because our frequency has increased. However, for ozone, we also see this increase in the longer duration events, and a similar story here for PM 2.5 events, that by the last 3 decades of the century, we have an increase in the number of 3 to 4 and 5+ day events relative to the beginning of the century. We can ask the question of how much of that is just because the frequency has increased in the way we defined our threshold. And so we're trying to get at this question by taking a slightly different tack where we say, what if we just take the top 10% of summer days, in this case for PM 2.5, and look at the average duration that those events stay above that sort of upper 10 percentile level. And what I'm plotting here is for each of our regions, the beginning of the century, so it's a three decade, three ensemble member average, beginning versus end of century. And we see that in the mid-Atlantic, there's almost a full day increase in the duration of these events by the end of the century. To finish up, in the spirit of this conference, we thought it was also interesting to think about whether these events are co-occurring. And so these are our time series of our principal components for our 3 variables in a random summer 2083 in one of our ensemble members. And so I think there are wiggles where we could argue that these things are co-occurring, and then sometimes they're lagged by a day or so. And so I think this raises a lot of interesting questions of physically or meteorologically and maybe chemically kind of what controls the progression of whether these are concurrent or sequential events. And so I'll just quickly highlight that we're not the first to think about this. Jordan Schnell and Michael Prather have a nice paper where they use the observational data to think about these offsets between occurrences of extremes in these 3 variables. Okay, so to end up, I just thought I'd mention, so I've kind of very quickly here laid out the approach that we've been taking in order to think about mining larger data sets and pulling out information hopefully relevant for pollution and temperature extremes from these massive, thinking towards the future if we have full chemistry large ensemble data sets, and even at present with medium ensemble data sets. And our ongoing work plans to look at some simulations we have available from collaborators at NCAR that are similar to the ones we've done in the GFDL CM3 model. And another part of this broader project is also thinking about trying to bring this information to the scales that are more relevant for local and regional air quality decision makers. And that is that we're somewhat strategically trying to go in and pick years to downscale to get that spatial refinement that then we can place a limited set of simulations with the EPA regulatory air quality model in the context of these larger ensemble simulations. So thank you.
Thanks, Arlene. Again, we are skipping Q&A to save time. Our next speaker is Dean Como, who will be talking about persistent summer circulations.
Okay, thank you very much. So I'd like to talk about persistent summer extremes. And when I refer to persistent summer extremes, I basically both refer to these prolonged hot and dry conditions, as we've seen, for example, last year in Europe. And they can, of course, lead to very high impacts to agriculture. But I'm also very interested in these stalling cyclones. We've seen both extratropical cyclones and tropical cyclones. For example, Harvey was such a stalling tropical cyclones remaining for 5 days in a row near Houston. And then, of course, you get very massive rainfall, total rainfall amounts and floodings. So I think it's these type of persistent extremes are very, very important from an impact point of view. I'm not going to talk about impact here. I really like to talk about some interesting trends, both in climate models and in observations that I think are relevant. And I will discuss some possible drivers behind those trends. Okay, so let me start with this picture. So this is actually showing simply the surface warming trend in summer since 1979, comparing here area interim versus the CMIP5 multimodal mean. And the unit here is scaled versus the global mean trend. So this means that the value of 1 referred means that that particular grid point has been warming at exactly the same rate as the global mean. And then, of course, you see that the oceans have values smaller than 1, they have warmed less. And land regions have warmed much more in summertime. So this is, of course, what we expect. And then you see these hotspot regions highlighted in black. For example, the Eastern Mediterranean, Middle East. So probably this is a well-known hotspot of climate change. And this is likely related to soil moisture feedbacks. I'm not going to talk about that here today, but I'm interested in that high latitude land warming that you see. So these black regions in Canada, Greenland, and large areas over Siberia. And the reason is because I think they are important for changes in summer circulation in the mid-latitudes. I'll come back to that, but let me first say a little bit why I think we do have these so pronounced trends in these high latitudes. I think that is related to snow cover changes. This is a recent paper by Connolly et al. That just appeared. It's showing that we have really extensive downward trends in snow cover in JJA, actually minus 80,000 square kilometers per year, which seems like a very big number. And that has actually occurred in exactly these high latitude regions. And that can be seen if you kind of map this picture on that one. So this shows the snow cover duration, so the number of months that you have snow cover, and this is the climatology. So basically red and orange regions have a snow cover duration of 9 months, meaning that only in summertime they become really snow-free, or by end of summer. So these regions are really sensitive to variability in snow cover in summer and long-term trends in summer. And we've seen very strong downward trends in summer snow cover. Good, so this is still a bit of a hypothesis, and actually in my view there's surprisingly little literature on this, where there's lots of literature on sea ice and its influences. But snow cover and its influence on summer circulation, there's really not much out there. Anyway, my hypothesis is that these downward trends in spring, early summer snow cover, they drive that enhanced high latitude land warming, via albedo feedbacks, via soil moisture feedbacks. And well, as I already mentioned, I think that I believe that this is important for changes in mid-latitude summer circulations and possibly also persistence. Good, so one thing, of course, if we have that high latitude land warming, then the poleward temperature gradient in the mid-latitude reduces. And this can actually also be seen in reanalysis, and you can apply simple thermal wind balances to it. And you see that the westerlies are weakening, so this is detectable signal. And next to the westerlies, also the storm tracks in summer have been weakening, and actually much more pronounced than the westerlies. And this is something that the climate models also project, but only under much stronger greenhouse gas forcing. So this is under RCP 8.5, and then you see that in summer, JJA here, by the end of the century, you also see the pronounced weakening of summer storm tracks. And by now, actually, there has been a lot of literature on this, so I would like to say that this weakening summer circulation is really a robust feature associated with greenhouse gas forcing. This is supported by model simulations, by observational analysis. We have a good physical understanding, and it's really also documented, well, in many papers now using really multiple metrics. Metrics, how you define your storm tracks. You can use eddy kinetic energy, you can trace individual storms, or you can use other types of metrics, but they all confirm that result. So I think this is a really robust thing. The question is, of course, what will this mean for weather conditions and persistence of weather? And this is something that Peter Pfleiderer has been looking into in recent studies. Recommend you to go to his poster. This is the wrong number, but still go to his poster. So then you learn all the details. I'd just like to highlight a couple of things here. So what Peter does is basically a very straightforward metric to define persistence, where you divide your days into warm days and cold days. And you use the median as threshold, and that is the median of the current climate. So also if the climate warms, you still have 50% cold days, 50% warm days. And then you can look into duration of consecutive warm days, consecutive cold days, etc. You can do something similar for rain persistence and dry persistence, defining threshold in the amount of millimeters of rain. And then you can also start deriving what we like to call warm compound nature, so really consecutive warm and dry days. Okay, these two figures below show a model validation. So this is we've been working with the HAPPY set of climate models. So this is an AMIP style simulations at present day climate and also at 2 degrees. And it really consists of several models and many ensembles, which is useful. And it compares fairly well with this observational data set. So this shows the warm persistence. So a typical value for warm persistence is about 5 days, climatologically. But then, of course, you see these regional patterns. The models do seem to underestimate persistence in Central Europe a little bit, but that might also be a sampling issue in the observational data. Anyway, in general, a fairly good agreement. Now, it's interesting to see, of course, how will persistence change in a warming climate. And this is comparing a 2 degrees C world minus present day. So present day is about 1 degree C. And then you really see systematic increases in persistence. And you see that in warm and dry, and rain persistence. And this is really averaged over all mid-latitude regions. So I should probably explain that scale a little bit. So this shows the relative change in exceedance probability of a particular period, right? So for example, if you have here 14 days, so 2 weeks, and then you see 50%, right? So in a 2 degrees world, there's a 50% increase in periods of at least 14 days of consecutive rain. So this is really quite pronounced, and this is a mid-latitude average over land. If you look at the other changes in persistence, it's more moderate. But of course, if you go regional, and again at Peter's poster, you can see all the details. But this shows it, for example, for Central Europe, which happens to be a region where we see more pronounced changes in persistence. We've also done analysis looking into what drives this, and that indicates that indeed the weakening of summer storm tracks is an important driver of especially warm and dry persistence. And for rain persistence also, because of thermodynamics, actually the total number of rain days will increase in a warmer world, and that is partly also responsible for that increased period. Okay, so now let me go back to that, that high latitude land warming again. So as I mentioned, this is weakening the thermal gradient in the mid latitudes, but it's actually strengthening the temperature gradient north of it, right? So really at that boundary from land into the Arctic Ocean. And that favors the formation of Arctic front jets, or if we look at the zonal mean in these type of double jet regimes. This is a picture from Tachibana et al., which analyzed those double jet states. And you see you have a very confined and sharp subtropical jet, and at the same time in the high latitudes that Arctic front jet around 70, 75 north. And these double jet regimes are associated with blocking in the mid latitudes. So this is shown here. So this shows the probability of blocking during such double jet states, right? And it's substantially higher than under normal conditions. Now there's different ways how you can look into that. One way is to explain that enhanced blocking is via waveguides and resonance. So the topic, the stuff Kai Kornhuber talked about yesterday. And the reason for that is that with those double jet states, you get actually a very confined and sharp subtropical jet, as you can see here. So this is an Hofmüller diagram, which Olivia already introduced earlier today. But now here we have on the vertical latitude and on the horizontal time. And this shows the westerlies. So you go from a broad single jet regimes to in early summer, June, to this double jet state by midsummer, and you see that the subtropical jet is a very sharp and confined jet. And it is well known that these type of jets can act as waveguides, and that is also shown in this picture below here. Good, and if you have such waveguides, you can much better maintain the energy of the waves, and you can create these type of circumglobal waves. So again, this is this wave 7 pattern. As Olivia also highlighted, this is likely a very important pattern in creating persistent summer circulations and persistent extremes. And it has that typical footprints in surface temperature, creating heat waves in important regions, which are also important breadbasket regions, as Kai explained. Okay, so there is a possible recent increase in these type of patterns. Kai showed that yesterday as well. This is showing a bit of a different plot, which highlights that especially the long periods that last 3 weeks or 4 weeks have really increased since 2000. So that is important to know. But yeah, these type of trends are quite metric dependent, so certainly caution is needed. Okay, so let me wrap up here. I'd just like to stress again that I think it's very important to understand what these type of, how these waves, these circumglobal waves, how they will change with global warming. They can cause these multiple heat waves and persistent cyclones around the globe, so really creating these concurrent extremes. And yeah, I've been talking about these 3 aspects mainly, so enhanced land-ocean contrast, the importance of that, the role of snow cover potentially in here, weakened background flow. I think this is a very robust thing for summer. Don't mix this up with winter, totally different processes. Waveguidability, which many people have mentioned here today and yesterday as well. But then there are also other mechanisms that are important. Enhanced monsoon forcing, we're looking in that right now. There's a 2-way interaction of these waves with especially the Indian summer monsoon. And that is important. And the Indian summer monsoon amplifies with warming. I'll wrap up. Okay, well, I'll just leave it to this, but come to me if you have questions. And one thing, I also have 2 postdocs positions available for everything.
Thank you so much, Dean. Our next invited speaker is Sarah Perkins Kirkpatrick, and she will be talking about global heat trends and heat waves. This is yours, right?
Okay, good morning everyone, or good afternoon, whatever the time is now. I must confess this probably isn't my best work of my career to date. It was a mad rush to submit this publication before I had my second child, and it's only upon reflection, some very sleep-deprived reflection, that I could have done this work a whole lot better, and also some very helpful reviewer comments. We recently submitted this paper to Nature Comms, and there are some good reviewer suggestions that I really want to work on. So I'm also happy to talk to anyone here about any ideas they might have so I can make this work a little bit better. So what this work was trying to achieve was to improve on what we know about how heat waves have changed. Previous work of mine has shown how heat wave days and heat wave intensity and heat wave frequency have changed. This was done a number of years ago, back in 2012. These are two of the figures from that respective paper, and as you can see, we claimed this was a global change in heat waves, but the grey areas indicate where we don't actually have any data, at least in this data set. Also with this data set, it was quite clunky. The resolution was about 300 or 400 kilometres, so it's not really that great for impacts. The pro of this data set is it's actually quite high quality controlled, so it's the data that we have is quite good data. On top of this, when we have heat waves, they don't just occur by heat wave days or heat wave intensity or heat wave duration. They're all combined. We tend, at least to date, we tend to break up these sort of characteristics of heat waves and look at their trends or any sort of indications separately. But obviously, that's not how they occur. So what we also wanted to do is see if we could, look at some sort of measure of cumulative heat wave, a cumulative heat wave index over a particular heat wave season and look at how those trends are changing. And we were also thought at the time this was really interesting for an impacts perspective. We hadn't actually had the time to really consult anyone in that sort of field, so that's really what I want to work on in the future as well. So the approach to kind of improve our knowledge on how heat waves have changed, we decided to look at the Berkeley Earth data set. So this is a 1 by 1 degree, mostly observational data set that covers the whole world, at least the land surface. It does go back to 1880, but we did not look at trends that far back because there is a lot of data missing the further in time you go back. We looked at daily maximum temperature. So when we derived heat waves, if you were here if you were here for the panel, you would have heard me say there's many different ways to measure heat waves. That still stands. So I'm not going to tell you which is the right way to measure them, but I went back to the definitions I've used in the past. So this was using daily maximum temperature. A heat wave had to last for at least 3 consecutive days in a row, and a heat wave day was considered when it was above the 90th calendar day percentile. So it's a seasonally varying threshold, but we only looked at events within a 5-month summer. So in the Northern Hemisphere, that's May to September. Where I'm from in the Southern Hemisphere, that was November to March, because heat waves can occur out of that really hot part of the year as well. When we looked at heat wave trends to measure how they're changing, we used the SENS-Kendall slope estimator. We also looked at a number of different heat wave characteristics in the study, but I won't necessarily talk about all of them today. So a measure of frequency was the number of heat wave days across the season. I used to use a lot of acronyms actually for these characteristics, but I'm trying to shy away from that now. We looked at the length of the longest event as an indicator of duration, and also the hottest heat wave day as a measure of intensity. Now that sort of new measure that we decided to look at was the cumulative heat exposure, and the way, this is probably where this study kind of falls down a bit, the way we looked at that was just simply summing the intensity of all heat wave days over that 5-month summer. So a lot of the time the values we got were quite high, and you will see that in further figures, but it was basically measuring how much heat do these heat waves generate over a season. That's what we were trying to measure, and with the idea that further work from this sort of metric could go into impacts perspective, and that's also bringing together the correlated nature of different heat wave characteristics. On top of this, we wanted to look at how the makeup of this cumulative heat exposure was changing. So another sort of crude way we did this study was breaking down cumulative heat exposure in terms of average intensity and heat wave frequency measured by heat wave days. So this was simply measured, well, that doesn't look like it should, but anyway, by looking at how the percentage of heat wave days change over time within part of this metric. So it was decomposed as you can't quite see well there, and also the average intensity. Now, the percentage, I want to stress here, because this didn't quite come, it wasn't quite clear to the reviewers of this manuscript. The percentage, for example, of days that contribute to this cumulative intensity is important, because say it could be 70%, which is really quite high. It's whether or not that percentage changes over time. So for example, heat wave days contributing more to contributing more to cumulative heat exposure than it used to, or is the intensity of heat waves driving this index more than it used to? That's what we're trying to answer. On top of this, not only with cumulative heat exposure, but also with the other heat wave metrics, we wanted to see whether or not their trends are accelerating over time. This is reasonably obvious that they probably are, but we wanted to see by how much, and really whether or not that result is significant. So can we really trust heat wave trends over the last 30 or so years, or is there a reason why we might not be able to? So just to compare back to the older data set that we were using, on the left is the HAD-GH C&D data set. That's the data set I used to look at heatwave trends prior. Again, grey areas indicate where we don't actually have any data. On the right is the Berkeley Earth data set, and you can see, at least eyeballing these figures, that where those regions have data, where they both have data, the trends are quite similar. So not only the fact that they're significant, which is indicated by the hatching, but the magnitudes are quite similar as well. Of course, over some of the regions where only Berkeley Earth has data, there's a lot of quite high significant trends. There might be some uncertainty around that because there's not a lot of observations, at least in the past, over those regions, but we do have a lot of confidence in a lot of areas using the Berkeley Earth data set. So these trends are looking from about 1950 to 2014. The HAD-GH C&D data set stops at 2014 currently. The message here is pretty similar to what we've said before. Heat waves are increasing in their frequency, intensity and duration almost everywhere. Obviously that significance and the magnitude of those trends do differ depending on the region. But unfortunately there's no change in the message that heat waves are getting worse. Now if we extend this analysis to the cumulative heat exposure, you can see that especially for the tropical regions, we actually are seeing quite large changes. Again, these trends are looking from 1950 to about 2014, I think. And there's a lot of significance over Eurasia, Southern Australia, and particularly Africa. Now, we need to keep in mind over these subtropical regions, they have a low temperature distribution to begin with. So when we have an exceedance of that particular threshold, it doesn't take much for that exceedance to actually occur. This has been documented in a lot of papers, not just by work I've done, that we see a lot more heat waves occurring in these regions simply by nature of the definition. So whether or not this actually means something for an impacts perspective, I've heard different points of view about it, but that's why we tend to see a lot of changes, a lot higher trends in those regions. So over those regions, if we're looking at, for example, a trend of 120 degrees Celsius per decade, that means that the heat waves are contributing an extra 120 degrees Celsius total per decade. So that's the extra temperature that we're experiencing when we actually see heat waves overall. The figures down the bottom are showing how the average intensity contribution is going down and the heat wave days contribution is going up. So basically what this is saying over this time period is when we look at the cumulative heat we're experiencing during heat waves over a season, it's mainly driven by the increase in heat wave frequency, not necessarily their magnitude. It's not to say heat waves aren't going up in intensity, they are, but the cumulative heat exposure is largely due to the fact that we're having more heat waves in general. And I'll go on to show that a bit more further on. Now, just of interest, we just wanted to also show what was the hottest cumulative heat wave season, or what was the hottest heat wave season that we've had, and when did this actually occur? So looking at the figure on the left, again, these tropical regions are experiencing the hottest seasons. That's no surprise there, especially over the Middle East. But the year of occurrence is also showing that most of these really hot seasons have mostly occurred on or after the year 2000, so really in the last 20 or so years. That's not true for everywhere, but for most of the globe, the hottest seasons have occurred in the last 20 or so years, which is consistent with the hottest summers we've also had, or hottest years we've also had. So what we also wanted to do for this study, and hasn't really been done in a consistent way before, is break these trends down regionally. There are a lot of papers out there saying, or looking at heatwave trends over Australia, for example, or Europe, but every paper's really used a different metric, and we wanted to we weren't expecting the results to be too different from all these different studies, but at least provide this in a one-stop shop using a consistent metric and framework. So this is looking at heatwave days. I won't go through this for every single index, but I will for heatwave days and cumulative heat. This is just this figure is showing a simple time series of various different regions and also the global average of heatwave days. So obviously there's a trend there, we can see it. There's a lot of interannual variability, but ultimately the frequency of heat waves are going up. There's no real surprise there. However, what do these trends look like when we look at various different points in time? So some of the research I did going into this study was if we look at average temperature trends, they're usually believable when those trends are about at least 17 years long. Okay, so if you look at a 10-year trend of average temperature, you're not really going to believe it, but if it's 17 or more years long, then it's more significant and it actually has some sort of believability to it. And I wanted to look at whether, does that hold for heat waves, or do we need longer or shorter trends to have some sort of realistic meaning? So we expected that trends from the later part of the time series would obviously be higher. There's a lot more warming going on. That's pretty easy to see from the figure. But as I've just explained, that's what happens. We do see higher trends as we move further in time. The trends in bold there are significant trends. So for most of the world, if we look at most regions of the world, if we look at heatwave frequency, these trends are relatively significant between 1970 and 1990. What I haven't showed here is from about 1990 onwards, these trends start to not be significant. So that's kind of shown in this figure here. I've just circulated trends starting from 1990 onwards. There's a lot of variability going on. The influence of variability on heatwave trends isn't surprising. We have documented that before. But what I wanted to drive home in this paper is we can't trust heatwave trends that are at least that are 20 to 30 years long. They have to be longer than that to account for variability. Heat waves are much more influenced by variability than average temperature, and I don't necessarily think that's something that's well understood from from impacts researchers and stepping out of the climate sphere. So we really wanted to drive that point home. As you can see, there is regional variability in the strength and the significance of that trend. The first row there is showing trends over Central North America, and that non-significance from 1950 is largely due to the warming hole over that time. So that's not, again, it's consistent with previous studies as well. So moving on to regional cumulative heat, again, you can see that sharp increase in both regional and global average time series from about 1980, 1990 onwards. And once again, trends become less significant. So I should have mentioned earlier, the dots on those trends are when trends aren't significant. Okay, so if they've got a dot there, a trend starting from that year doesn't have any statistical significance. It might be high, it might be alarming, but it doesn't. We can't really believe it, so to say. So the trends. It is the same slide. So I just wanted to put the world map up there to just bring you back to the fact that when we're looking at cumulative heat, it is largely driven by heatwave frequency. You can see on the left there we've got figures of the time series. Intensity is increasing. It is a bit hard to see in that figure, but for most parts of the world, at least from 1950, there is a significant trend. It's just the scale of the y-axis that kind of throws it there. But yes, this cumulative heat measure, at least how we've devised it, is driven largely by heatwave frequency. So I just wanted to demonstrate that with this schematic. You've got your time series here of temperature. I can't draw very well in PowerPoint, as it turns out, so just bear with me here. That green line is the threshold, the temperature threshold for heat waves. If we shift our frequency metric up just by a few degrees, which is indicated by the red line, you're actually starting to see now heat waves that didn't occur before, which is why we're having larger frequency of heat waves, and also some heat waves are actually becoming longer. And interestingly, what can happen, I haven't quantified it, but what can happen is if you look at the heat wave in the orange circle, it would have a lower average intensity than many of the other heat waves there, but it's still a heat wave based on this definition. The average intensity of the heat wave indicated by the purple circle would also likely be less than what it was. It's gotten longer, but we don't have as hot a days contributing to that event. There are some events there that would obviously be hotter than what they were before, but this is why the average intensity is likely contributing less than what it used to. So just to conclude, there is no new news here that no matter how you slice and dice it, heat waves are increasing. We've just shown that that's still happening and accelerating at the same time. Cumulative heat is the most extreme in subtropical regions, and most of these extreme seasons have actually occurred since in the last 20 years. The largest trends that we see are in heatwave days, and I really want to drive the point home that internal variability or even interseasonal variability really makes heatwave trends less useful within a 30-year period. I did just demonstrate this for heatwave frequency, but even when we look at intensity or duration, a 30-year period sometimes isn't enough. I just wanted to put up there my to-do list. So as I said, it probably wasn't my best work without a few months of reflection. But something that came out of the reviewer's suggestions was to use a degree days type approach, which may be more useful for an impacts purpose. I'll leave it there.
Thanks, Sarah. Again, sorry for the fact that we don't have time for Q&A. With that, we'll close the session on sequential and persistent events. And I hand it to Susanne.
You need to switch the slides.
This is a question for on the presentation, a couple of slides. Oh, sorry. So this was a question for Dim and for, I guess, for Kai as well. I'm curious about why you all generally tend to focus on summer, and are the dynamics different during the winter season? Is that why you haven't looked at some of these extremes during the winter season? Just curious about that.
Yeah, so I mean, I guess initially it was kind of, we started this work out kind of a bit impact driven, I guess, and these events are happening in summer, so that got us started. But yes, the dynamics in winter and summer are really fundamentally different. And so in summer you tend to have much more zonally oriented jets, weaker jets, and of course there's much more interactions with the soils also, and by SSTs. So yeah, I think it's really quite fundamentally different. And also if you discussions about the role of the Arctic and sea ice and snow cover, then I think these are really two parallel discussions where winter processes are really fundamentally different than in summer. In winter, things happening in the stratosphere, SSWs, and the role of sea ice possibly on that is is a discussion, and that is important. But such processes are not relevant in summer, for example. Yeah.
Okay, so let's start the new session on correlated streams in traditional disciplines. And the first talk will be on floods by Amir.
All right. Thank you very much. So I'd like to acknowledge my co-authors. And from this group, Gianfausto Salvadori is here. The rest of them are not here today. As was mentioned a couple of times by Thomas, Ivan, and others, in coastal areas, we can get flooded by the ocean or from land. We call it terrestrial flooding or fluvial flooding. And they can happen together at the same time, right? Especially if there is a hurricane, obviously extreme rain and surge, they happen together. But we don't necessarily need a hurricane to experience compound flooding. High tide happens on regular basis, and even if there is not one big event that drives both, you can even randomly see high tide and above average river discharge and see the compounding impact. The amount of water that rivers can drain into the ocean is a function of the gradient, right, between the water levels, right? And the higher the water level, obviously, the less water can drain. And if you have really extreme surge or really extreme tide, water can even go backwards and create backwater and worsen flooding. So that's why we are interested in this. The issue is that if you look at guidelines, it was mentioned yesterday, like for example, USGS guidelines in the US for flood frequency analysis, it's based on river flow data. We ignore the dynamics of the ocean. If you look at NOAA's guideline for ocean water analysis, frequency analysis, again, we ignore the dynamics of the riverside. FEMA has an approach that I'll talk about it in a moment. So in coastal areas, we are interested in the interactions. And yesterday and also today, we talked about different types of statistical methods on the hazard side, linking multiple drivers. I'll briefly start with that, and then later I'll connect this to a physical-based approach, a process-based approach for linking statistical and numerical modeling of flooding. So let me start with the hazard type. So we did a study of major basins in the US, looking at the interactions between ocean and fluvial flooding. So first we started with a hazard approach where you want to link different drivers and understand the relationship. We need to start with a kind of so-called hazard scenario. There are different types out there. For example, the or hazard scenario, which means if you have, let's say, one driver, river discharge, and another one, ocean water level, you have like two critical thresholds, one for ocean water level, and another one for discharge, and observations that are above these two thresholds are all considered as events that you really care about. There are other types like Kendall, and so forth, but this is what I will show in a moment. So we looked into different places. This one is Washington, D.C., San Francisco, and Philadelphia. There are more. So these are like observations, and we used copulas to relate these two together. Again, I don't go into details of this part. The publication is available. So this allows you to, for example, see, let's say, a 20-year return period univariate river flow on the x-axis, and the same on the y-axis corresponds to what type of bivariate return period. For example, 20-year event, 20-year can turn, for example, 16-year event in this case, or 13-year event in this case. Okay, so our idea was to somehow translate that into something that that the impact community can really understand. So we use this widely used concept of reliability or failure probability, which comes from reliability theory, and it's widely used for design purposes, for engineering purposes, and extended to 2 dimensions. So in the univariate dimension, this is the general equation. P is probability of occurrence, and T is design lifetime. You want, let's say, to build something that for 50 years or 100 years. So if you plot that failure probability against design lifetime, you'll get a curve like this. So the idea was to extend this kind of univariate to a bivariate for 2 hazards, but you can do this for more using copula functions. With that, then you can have one for univariate and then another one maybe for bivariate case or two hazard drivers. So this is an example for Washington, D.C., where this is your univariate, typical univariate flood hazard based on USGS guidelines. If you get flood frequency from them and then do this kind of reliability, this is how it would look like. And then if you bring the ocean flooding component, you will see that the failure probability increases. By the way, failure probability doesn't mean physical or a structural failure. It means you design something for a certain extreme. If you get to that or exceed that level, it's called theoretical failure. But this, if it's a structure, it doesn't necessarily mean physical failure. And we also did this with sea level rise. We have already sea level rise projections, so you can bring that, add it to your ocean flooding, and look at the failure probability under different sea level rise scenario. And that's the purple line here. So these are different ways of describing how your flood risk will change if you consider multiple drivers versus the typical traditional way of one driver at a time. So we did this for different locations. Let me skip this. So we have a method that gives you this sort of multi-hazard scenario, right? So you can generate bivariate return periods, like what is your 50-year, for example, combined ocean and terrestrial flooding or fluvial flooding. Now, what is next? So this is the hazard part. Ideally, you want to link this to a physically based model that can describe, okay, what does it mean in terms of flood extent? So that's the next step. So that means you need to have a physically based model and use these sort of hazard scenarios. There are infinite combinations here of ocean water and terrestrial water level, and test it basically and see what's your flood extent. Again, there are many, many different combinations here, right? So in the US, FEMA has a guideline that is informally referred to as a kind of conservative way of addressing this issue. And the guideline kind of tells that if let's say you want to get your 100-year flood in a coastal area, you find your 100-year flood peak, you run a model, you get a profile. Let's say this is your water profile for 100-year flood. And then you do the same thing for ocean, but separately. You do this for the ocean, water level. So let's say you get this profile, and then you connect these two, and that's considered your flood extent. But the FEMA guideline is not very specific. It doesn't tell you if you use 100-year flood in the upstream, what kind of downstream condition you should use. So most people use long-term average, and the other way around. When you use extreme 100-year ocean flooding, they use long-term average discharge. So this is kind of considered as the latest guideline that we have here. Again, it's not very specific on the boundary conditions. So in a moment, I'll show you that even this approach can lead to some kind of underestimation of compound events. So now I'm going to link the two together. So first, again, as I mentioned, this is from Salvadori et al. Paper. There are different types of hazard scenarios, right, that you can pick. This is the OR hazard scenario that I mentioned. If you're interested in exceedances, concurrent exceedances above two different thresholds, this is called considered AND hazard, right? So I mainly talk about these two in the rest of my talk. So what our approach is that, okay, we have a system. This is an example of Washington, D.C. Sorry about that. This is an example from Southern California. This is Newport Beach area. So we have, again, ocean water level, and here we have a river discharge. And here I have two different curves. One of them is, again, joint return period based on OR hazard scenario, and the other one is AND hazard scenario. And this one, OR, is more conservative because either one of the two drivers can cause it as considered really extreme. So now if we run a model, and here we are running a two-dimensional hydrodynamic model, where here this is the water profile, but I'm showing only one dimension here. So if you run ocean water level alone, this is the profile you get. If you have river discharge alone, this is the profile you get. And if you combine them together, sorry, for some reason, the other one is not showing up, sorry. Right. So if you combine this red and blue, then you will get the kind of FEMA guideline. And here, we show that the FEMA guideline compared to a kind of AND scenario and even an OR scenario, it will underestimate flood water level somewhere in between. Not at the boundaries where we use extreme, but in between we will under. So here are examples from other places, but let me summarize here what we do in our kind of hybrid statistical hydrodynamical model. We start with a statistical approach for identifying different types of hazards, and we go with AND and OR. We explore both, but looks like OR is obviously more conservative. AND seems to work really well, at least in our cases. So we generate profile based on FEMA approach of two extremes on each side, linking them together, and then we use AND hazard scenario to get the updated flood risk profile. And if you have a hydrodynamic model, you can easily translate this to flood extent. So not only you get your hazards and your drivers, you can map your flooding, compound flooding events, and simulate the effect of back propagation and everything in a hydrodynamic. This is again an example from Southern California, and this shows water depth, and we have compared this also with FEMA method, and we show that somewhere in between, FEMA's approach underestimates flood risk and doesn't capture fully the compound event. So the source code of the method is available on my website. There are two toolboxes. The last one is pretty new. So it has a graphical user interface. Also, the source code is available. You can very quickly and easily generate the hazard scenarios I mentioned, by value return period, and use this as inputs to a model. And this is my research group. They do the hard work.
great talk. I'm sorry I have to move on to the next one. So next talk is by Deepti Singh, Concurrent Regional and Global Temperature Extremes.
Thank you. Just want to thank the conference team for putting together such a fantastic workshop, and I also want to acknowledge some of my co-authors, two of whom are in the room, Justin Mankin and Dr. Radley Horton, who have done some of this work with. And I think I was a little optimistic when I submitted this, the abstract for this, so I'm really going to mostly focus on regional extremes. I haven't really completed too much of the work on the global scale extremes. So since we haven't really agreed upon definitions for some of these some of the events that we've been talking about during this conference, I thought I'd throw in my definitions into the hat as well. So when I think of concurrent extremes, I think about extreme events that are occurring at the same time. They may not be in the same location. And then when I think about correlated extremes, I think about extremes, even though they're not occurring at the same time, they're related by some physical process. And so concurrent and correlated extremes would be extreme events that occur at the same time and are related by some physical mechanism, even if they're occurring in different locations. And so, these concurrent and correlated extremes are different from extreme events that might occur at the same time simply by chance. And so what I'm going to talk about today is our concurrent and correlated extremes that affect North America during the winter season, and they've had some particularly important societal impacts in the recent winter seasons. And then briefly introduce some of the work that I'm doing to extend this work on a global scale. And so some of the work that the first study that I'm going to talk about was really inspired by or motivated by the impacts that opposite extreme events were having, that opposite extreme events occurring across the U.S. were having on the national economy. In particular, in the winter, we've all probably heard about the California drought. And so in the winter seasons of 2013-14, there were extremely warm conditions occurring over the western U.S. that amplified the dry conditions that were already existing there. And then on the eastern, on the eastern side, we were getting kind of hit by these consecutive snowstorms and really cold, cold air outbreaks coming from the Arctic and causing unusually cold conditions. And so in the western U.S., we had impacts on agriculture, water scarcity, as well as wildfires. And then on the eastern side, these kind of snowstorms affected transportation and infrastructure. And the events that were associated with these kind of extremes ultimately led to sort of billion-dollar weather disasters during these multiple seasons. And as we heard about from Dr. Oppenheimer on Tuesday, even though these events are occurring in different regions, they're still connected by the national economy, and so they can have sort of compound impacts on disaster resources of federal aid that is available to manage these kind of disasters. And so specifically, talking about this pattern of extreme events that were occurring across North America in the winter seasons of 2013-14, 14-15. This is just an example of a surface temperature anomaly map for a few days during February 2015 when this pattern was particularly prominent. As you can see, there's much of the western U.S. was covered by warm temperature anomalies, and much of the eastern U.S. was covered by these extremely cold temperature anomalies. And these anomalies, the magnitude of these anomalies exceeded 12 degrees across some of these regions. And so following what we were talking about on Tuesday, these kind of opposite extreme events have impacts not just on humans, but on other species. So this is just, I lived here during some of these events, and this is a very a grumpy dog that I had who had to, getting ready to go out in some of these cold events. And on the right side, even though she looks happy, some of these extremely warm conditions can have physiological stress on our other species, I guess. So basically, I ask three main questions associated with these kind of dipole extremes. The first one is, are these dipole extremes becoming more frequent? The second question is, are these associated with dynamical changes that have occurred in the climate system? And the third question is whether anthropogenic climate change has influenced the likelihood of these kind of events. And so I have the answers here in case you need to leave for lunch. But I'll provide some of the evidence for this in the following slides. We first defined a metric to capture this kind of spatial pattern, and the way we did that is by classifying a day that has warm extremes exceeding daily maximum temperatures exceeding some warm threshold in the western U.S. at the same time daily minimum temperatures falling below a certain cold threshold over the eastern U.S. And so a dipole day would be when some minimum fraction of these two domains were affected by either warm extremes in the west and cold extremes in the east. And we define the intensity of these events as the difference in average temperatures over the regions that were experiencing extremes in these two domains. And so this plot here shows you the frequency of these dipole events, and the difference between these lines are just the minimum area threshold we use to define these events. So the light blue line that you can see on the top are sort of moderate dipole events where only about 5% of these domains are experiencing these warm and cold extremes, whereas the red color here indicates more extreme dipole events where at least 30% of these domains are experiencing extreme events. So these are some of the more high impact extreme events. And just for the purpose of this talk, I've summarized the trend and the significance of that linear trend that we estimated for the more moderate 15% dipole events that are shown by the black line there. And on the right here is shown the intensity of these dipole events. And so what we can see is that there is an increase in the frequency of dipole events, and there's an increase in the frequency, in the intensity of these, there's an increase in the intensity of these events as well, although the increase in the intensity is not particularly significant for some of the more moderate events. It is significant for the higher impact dipole extremes that we identified. And so the increase in frequency amounts to about an increase of 12 events over this 36-year period, which is pretty significant over a short period of time. And so then we're interested in kind of understanding what are the circulation patterns that lead to these kind of dipole extremes. And so for the same events that I've calculated, as shown the trends here, we also create composites of these dipole events to then look at what the circulation patterns look like. And so what we find is that there's a pretty really beautiful wave pattern that exists pretty much across the tropical Pacific, from the Western Pacific across the Atlantic. We see this ridge trough pattern, which kind of represents an amplification of the mean winter state over this region. So there's typically a ridge over the Western U.S. and a trough over the Eastern U.S., which is why the Western U.S. is warmer. And the Eastern U.S. generally experiences more severe cold events. And so we've identified this pattern. And so then what we do is look at how the frequency of occurrence of these patterns, and then how often these patterns produce extreme events. So that'll become a little clearer as soon as I go to the next slide. So here, the black line shows you the frequency of patterns that look like the one I showed before. And there's no really significant trend in that. So basically what we're saying is that these changes in these dipole extremes are not associated with a change in the circulation patterns that cause these events. However, the red line shows you how often those same patterns are producing these dipole extreme events. And we find an increase of about 22% in these patterns producing these dipole extremes. And what that means is that it's not the dynamical changes that are causing these extreme events, it's more thermodynamical changes in the system. And more specifically, it's the fact that the Western US is warming faster than the Eastern US. And so when these patterns occur, overlapping that warming pattern, they tend to create an amplification of that mean state. And so next, we ask the question of whether these trends are associated with anthropogenic forcings or not. And to address that question, we use the NCAR large ensemble and calculate 36-year trends in the pre-industrial simulations and in the historical simulations. And then we look at, so these box plots represent, this is just an illustration of what we do. The box plots represent the distribution in these two different climates. And then we look at how, where the observed trend falls within these distributions. And so, again, for those 15% dipole events, if we look at the pre-industrial control simulation, what we find is that there's a 50-50 likelihood of getting either a positive or a negative trend when there's no external forcing on the climate system. But in the historical simulations where we have included the role of historical forcings, we find that there's a much higher likelihood of getting this positive trend. And the difference in the likelihood of getting that positive trend is significantly different, which means that, what we conclude from this is that historical forcings have made the likelihood of this positive trend, have significantly increased the likelihood of this positive trend compared to a pre-industrial climate. And then briefly, I want to talk about extending this work to the global scale. I have only one slide, so almost on time. What we've done is basically looked at the frequency of these, the fraction of area across the northern hemisphere, and then again across the tropics, mid-latitudes and high latitudes, and quantified what fraction of the area is concurrently experiencing warm extremes, cold extremes, and then these warm and cold extremes. The different colors represent the different regions, and what we find is that there's almost a doubling of the fraction of area experiencing concurrent warm extremes over the about 30-year period that we've looked at. And of course, the high latitudes have more extremes, and this is sort of kind of just representing the Arctic amplification of the pattern that we see in the climatological mean state. And we've done this for cold extremes, and this is no surprise. The frequency, the area concurrently experiencing cold extremes is going down, and the high latitudes have a much, stronger trend in that. That's no surprise either. And then when we look at some of the same warm and cold extremes, what we find is that pretty much, there's no really significant trend across most regions, but surprisingly, there's a significant increase in the concurrence of warm and cold extremes in the tropical regions. And so that's something. So I forgot to mention this is these are annually averaged values. So there's going to be seasonal differences, and so kind of this trend in the tropics is interesting, and we're sort of working on trying to identify some of the drivers of these changes, and whether it's different from just the sort of mean changes that we see in temperatures. And so to quickly summarize, what we find is that there is an increase in these opposite winter temperature extremes over North America, which is consistent with the influence of historical forcings. We also find an increase in concurrent warm extremes across the northern hemisphere. And so some of the obvious questions following some of this research is understanding how is the seasonality of extremes changing? Is it just which seasons are driving some of the changes that we saw on the last slide, and whether it is what's the role of natural variability versus external forcings in driving the trends that we've seen. So, with that, thank you.
The next talk will be about extreme climate over Europe from a paleoclimate perspective by Norel Rimbo.
Okay, thank you very much. The majority of talks in this session, in this workshop, was about climate extremes in present climate and especially in future climate. This talk is about the climate extreme in past climate. I hope you will find interesting. One problem we face when we analyze climate extremes is the shortness of observational period. We discovered that climate extreme indices show pronounced trends or decadal variability, as was presented also here. And I think that we better understand the processes behind this variation if we place them into a long-term context. Proxy data can help us to enlarge our perspective about climate extreme variability beyond observational period. There are a lot of proxy data available. Here, just to warm up a little bit the atmosphere, the paleoatmosphere, I just put here a section in a lake sediment core. If we count the flood layers in such a record, we can reconstruct the history of floods thousands of years before present. In the next, here it is just a section in a coral skeleton, and you can see the bands of animal growth, and we just measure various quantities from these layers, including delta O18, and relate them with climate variability. The same happened with the ice cores. You can see here they are visible, the annual layers of ice accumulation. There is a lot of work that relate this proxy data with, for example, with dominant mode of climate variability, like El Nino Southern Oscillation, or the North Atlantic Oscillation, or the Atlantic multiplicator oscillation. There is not much work trying to connect the variability in this proxy data with climate extremes. So here is my talk is focused on this aspect. I will refer to three proxy records that are relevant for climate extreme variability over Europe. The first, it is a lake sediment from southern Germany that records the floods of a small river Ammer, that extend back in time more than 5,000 years. I will discuss also the relationship between extremes and over Europe and the variability in two delta O18 records from a northern reciprocal and Greenland ice cores. Starting with lake sediments, the first exercise is just to see what are the extreme. The first, it is what are the extreme extreme precipitation pattern associated with flood in the location that I mentioned. First, I construct the time series of the observed floods, and I make the composite map of the heavy precipitation, the frequency of heavy precipitation rain for the flood years. As you can see, as expected, the frequency of heavy precipitation increased in the flood area, but in fact we can see that the area of increase of heavy precipitation extends from Western Europe to Southern Europe. Is not located only near the flood region. In the same time, over Northeastern Europe and Southwestern Europe, the frequency of heavy precipitation decreases during the flood years. The same exercise for extreme temperature index, that is the frequency of summer days, show a reverse pattern. We may conclude from here that the flood records, it's a proxy for extreme precipitation, not only locally, but it's a proxy for large-scale extreme precipitation variability and also extreme temperature variability. To better assess and confirm this result, we make the we make the composite map of upper level circulation. That this circulation is known that it controls the surface extremes. We make the average over all flood days. That means those days that is characterized by discharge about flood level. As you can see, a pronounced drought appear over Europe, but it is part of a large wave that extends downstream. The wave appear more clearly in the PV field. You can see it is a wave that increases in amplitude and eventually breaks over Europe. What is interesting it is that high value of PV are recorded exactly over the region where at the surface we have extreme high frequency of extreme precipitation, and relatively low value of PV are recorded over a region where at the surface we have low frequency of the heavy precipitation. That means that this is another confirmation that the floods record is related to large-scale extreme patterns. Now, going to the paleo context. Here is the time series of the flood frequency over the last 5,000 years, and here the observed time series of observed floods, the last about 100 years. As you can see, there is a lot of variability in the frequency of floods, but as a rule, we can see that during cold periods, the frequency of red bars, that means the frequency of floods, it's higher than during the periods when the climate was warm. For example, during the late Lycene, you can see a lot of floods, and during Roman warm period, the density it's low. So that the observational period doesn't seem to be out of range. It seems to be quite normal. If you count how many floods we have here, it is in between maximum and minimum here. So that as a rule, cold periods are associated with more floods, and warm periods are associated with less frequent floods. Now, what is the forcing behind this variability? What you see here is the time series of frequency of floods in a 100-year moving window. More than 60% of the variation of this flood frequency is given by two cycles. One of about 2.3 kiloyears and the other one of about 1 kiloyears. The same cycles appear in the solar irradiance forcing, and these are very well-known cycles. It is called Bray and eddy cycle. And the rule is the same. when we have low solar forcing, we have more floods, and when we have high solar forcing, we have less floods. What could be the mechanism behind it? Here I just put here the pattern of PV, and I select the years of high solar and the low solar, and I plot the distribution function of PV for the two cases. You can see that for the flat region, high value of PV appear more frequent than low value of PV, and here other way around. So this suggests, this shows that this pattern is enhanced during low solar forcing compared with high solar forcing. What could be the mechanism? The mechanism could be the following. When we have low solar forcing, we have more blocking, more frequent blocking here, and this blocking favor the wave breaking in this region, and because of this, more floods appear. Now, this mechanism is very well known as synoptic time scales. And we think that at the longer time scales, this mechanism is dominant and explain this connection. Now it seems that I was very, I have not many minutes left, so that here is going to the next proxy at Coral record. You can see that Coral because it's related to high frequency of warm events and low frequency of wet events over northern Europe, and this is explained by this pattern which shows a blocking over this region that favor cold conditions over northern Sea, and this is consistent with more frequent hot extremes and less frequent. Yeah, and it is related also to a wave, stationary wave that extends from North America to Europe. So I think I don't have time to go also to ice cores, but just to conclude, it is to combine this. To combine the proxy data with this relevant circulation for extremes like blocking, wave breaking, and quasi-stationary waves that are recently published, we can enlarge our perspective on extreme climate variability beyond the observational period. Okay, thank you. I will stop.
I think we have to move on to the next talk because we're so behind schedule. Get here. So the next talk is by our own Park Williams from Lamont, talking about wildfires.
Great, thanks very much. There are really three main ingredients in order to get an extreme wildfire. You need climate to be wet enough to grow abundant fuel to burn. You need climate to be dry enough to dry that fuel out to make it flammable. And then you need really strong winds to spread a fire. And in California, there are a lot of ways to put together that set of ingredients. And so in trying to figure out what happened in the past, it gives us a lot of freedom, a lot of knobs to wiggle in our mental model of fire, and may lead us down the wrong path from time to time. It's really easy, in other words, to think we know why fire occurred in the past. But those knobs also, or the amount of different ways you can get the recipe for fire, can lead to a really large amount of speculation in terms of what's going to happen in the future with fire, especially in California. And this speculation has been really motivated in the last couple of years by repeated, very extreme, record-breaking fires, record-breaking either in size or in destruction. In this talk, I'll be focusing on these regions here, In California, these are the more heavily vegetated regions where you have a lot of fire. And fire occurs mainly from May through December in really 2 fire seasons. It looks like one, but they tend to be driven by different things. I'll talk about that. One is summer, the May through September summer season, and one is in fall. At the end of the talk, I'll talk about fall. This is when the really big destructive fires that have been making the news recently tend to be clustered. And the reason, or beyond just the occurrence of really big destructive fires in the last couple of years, there's been an increase in the amount of fire activity over the last 50 years at least. This is a graph showing the annual area burned in California, and there's been an increase by a factor of 5 or so since 1972. The colors represent different seasons, and dark red is the summer season. And so what we can see here is that the increase in burned area is really due to a big increase in summer burned area. We can look by region, and we can see that actually the increases in burned area have not been occurring everywhere. The increases in California burned area are really due to increases in the North Coast region and in the Sierra Nevada region. And we can look further by land cover type and see that the increases are really due to forest fire area. If we look outside of forest fire, or outside of forests, we see a bit of an increase mainly due to non-forest area within the Sierra Nevada, which is a pretty heavily forested area. If we look outside of Sierra Nevada, then this is pretty flat. And so summer forest fires are really the cause of the increase in burned area in California. So we'll start by investigating summer forest fire, and we're going to look to see what drives variability in summer forest fire from year to year, and then how those variables have changed in the past, and if those changes in the past are consistent with what we expect based on climate model simulations. And so the ultimate story here is that summer forest fire is promoted by drought. On the left, we're looking at correlation between summer forest fire area and the vapor pressure deficit, which is the aridity of the atmosphere, and it is driven by temperature. And we can see the correlations are quite strong. If we look at the statewide correlation, here each dot represents a year, and we can see that forest fire is strongly promoted by high vapor pressure deficit. And the color of the dots represent time. Blue is before 2000, orange and red is after 2000, and the fact that we see the orange and red clustered in the upper right corner means that as vapor pressure deficit is increased, then the burned area has increased in a predictable way. In fact, the slope of just the blue dots or the slope of the orange and red dots is indistinguishable. And so the relationship between heat and fire has not changed during this time. This y-axis is a logarithmic y-axis, and this indicates that this is actually an exponential relationship. So each degree of warming has a larger impact on forest fire area than the previous degree of warming. Decreases in precipitation also drive increases in fire. It is interesting that that correlations with vapor pressure deficit are stronger than correlations with precipitation. We see that throughout the western United States. So what's happened so far with temperature and vapor pressure deficit and precipitation? Well, temperature, as the black line indicates, has increased by almost 2 degrees Celsius in California since the early 1900s. Vapor pressure deficit is increased by about 13%. These increases are statistically significant by far. And then the red lines say what climate models project or simulate should have happened as a result of greenhouse gas accumulation in the atmosphere. And so the heating and the aridification of the atmosphere in California is consistent, remarkably so, with what we expect as a result of global warming. Precipitation has been wildly variable from year to year and decade to decade. There hasn't been a long-term trend in precipitation. And climate models, this is warm season precipitation when fires are occurring most. Climate models project a slight decrease in warm season precipitation, but that trend should not have emerged as detectable as of now, and it doesn't seem to have. And so the conclusion is that the global warming process is increasing fire in forest fire in California summers just because of warming alone, and changes in precipitation have not really emerged as part of the story from the anthropogenic climate change perspective. When we look to non-forests during summer, so grasslands and chaparral areas, then the story is quite different. These are the same graphs that I showed last time, but now for non-forest areas. And we see that that fire in non-forest areas really isn't sensitive to heat and drought. And the reason is because these areas are fuel limited. If it's places that are, or if it's just hot and dry all the time, there's actually not enough new grass growing to promote fire. And so instead, if we look at the amount of precipitation during the previous 2 years, that's where we see the significant relationships. And we see the most in the areas that are less forested or more sparsely vegetated. And so the story here is that if you have a dry or a wet couple of years before the fire year, you actually load the dice toward bigger fires because you've grown some new fuels with that precipitation. After that happens, if there's abundant precipitation, then we do find that a dry and hot third year or fire year is an important secondary effect. So the perfect recipe for non-forest fire in California summers is to have 1 or 2 wet years followed by a dry year, and the fires will occur during that dry year. 2017 was a good example of that, where 2016 was pretty wet, and then 2017 and 2018 had big fire years because of hot summers. So what's been happening with precipitation? So basically what I just said is if you have an increase in the volatility from year to year in precipitation, that will promote non-forest fire. And that's what we've actually seen. This is a record of whiplash events where you have 1 or 2 wet years followed by a dry year. And we see that in the observed world, there's been quite a large increase. This is a statistically significant increase. If we ask the models what should have happened over the last century, they say that as of now, as of 2018, there should not have been an emergence of these whiplash type events. And so either the models are wrong, or what we've seen over the last century has arisen because of natural climate variability. It is interesting that despite the increases in volatility of precipitation and the increases in temperature, which should promote fire given that there was just a big wet year to grow new fuels, we haven't seen increases in summer non-forest fire in these areas that are the least forested in California. And that means that even if there was a big global warming component to the potential for fires, humans may have a big enough influence on the fire regimes in these areas to prevent big trends in forest or in non-forest fire from emerging. Finally, for fall fire is by far the most complicated and the easiest to explain away, given basically whatever story we want. The 2 main things that promote fall fire are strong offshore winds that bring dry air from the high desert, squeezing through mountain passes and pressurizing as the air comes to sea level. The air is very dry and very warm by the time it gets down to the foothills of Sierra Nevada or the coast. And as long as these wind events tend to begin occurring in fall and peak in winter, and the reason is because this is when high pressure systems develop across the high desert in the western United States. And if one of these big offshore wind events occurs before the onset of the winter precipitation season, which begins in fall, then that's the perfect recipe for fire. In the last couple of years, this is what we've seen occurring. So what might global warming be blamed for here? First, we can look at winds, and we actually see no trend in winds. This is the Fosberg Fire Weather Index, which is just an index of the dry windiness, and we see no trend since 1948 in either the frequency of big wind events or the mean intensity of wind events. If we look at what's happened with well-known Santa Ana wind events in Southern California, there's been no trend there as well. And according to theory, you'd actually expect a decrease in the frequency and intensity of fall wind events as global warming causes the continent to warm faster than the ocean, disrupting the temperature, the change in temperature gradient during the fall between the ocean and the continent. And so the story here is that global warming probably has not had a big promoting effect on fall fires through winds. How about precipitation? We really don't see trends in fall precipitation in California, except maybe in the South Coast region. This is a record of the frequency of wet days during the fall. We see a slight decrease in fall precipitation frequency that is consistent with a slight decrease simulated by climate models. And so perhaps there is some influence of precipitation, or of a decrease in precipitation in Southern California at least, in promoting fire, but likely not much. However, we do see that if we calculate 1,000-hour fuel moisture, which is just a mathematical calculation of a water balance, we see that there has been an increase in the frequency of days with low fuel moisture, or there's a decrease in fuel moisture, which is interesting because, as I said, there hasn't really been a change in precipitation. And this is due to warming. So if we recalculate this fuel moisture calculation, after removing linear trends in temperature and humidity since 1948, we see that fuel moisture, that the increase goes away, indicating that warming has dried out fuels in the fall, even though precipitation hasn't really changed. Importantly, these trends only go back to 1948. If we look at temperature and VPD, we find that over the last century, actually, there haven't been really big trends toward warming-induced drying of the atmosphere during fall over the last century. We see instead a lot of decadal variability, and since the 1940s, there's been quite a bit of increase in vapor pressure deficit, but since 1901, not yet statistically significant. However, the increase that we have seen, the slight increase, is consistent with what we'd expect based on global warming. And so this aridification of the fall atmosphere is likely to continue and emerge as a global warming impact in the next decade, even though it hasn't done so statistically significantly so yet. And so that means that even with no change in precipitation in the fall and no change in the mean state of winds in the fall, we're loading the dice toward larger fall fires, such as those we've seen in the last couple of years in California. And so I'll just conclude by saying that it's easy to speculate a lot about the impact of global warming on fire in California. But according to this analysis, what we see so far is that the very clearest impact is just by warming itself. Warming dries out fuels, and this has the biggest effect in areas where there are a lot of fuels, where you don't need to also have the special combination of wetness in order to dry the fuels. And the impact so far has been in the summertime when you don't need this special combination of extreme winds and abundant fuels and dry fuels in order to get fire. So there may be an emerging impact of decreased precipitation as well in Southern California, but by far and away the clearest influence is warming, and that's consistent with what climate models project to continue in the future. Thanks.
Okay, so while we transition to the next session, I'll open the floor for one burning question for the last four speakers.
Yes. And you said, yeah.
I just wanted to ask a quick question about this last presentation, which is, given that it seems easier to detect an anthropogenic signal in the summer fires, why do you is it just random that the last couple of years have seen these really bad fall and winter fires, or do you think there's some anthropogenic signal in the last couple of years of November and December fires?
But even without warming, the last couple of years have been extreme in terms of a late onset of precipitation, even in Northern California, where models do not say that precipitation should be delayed. So the last 2 years, delayed onset of winter precipitation combined with repeated extreme and prolonged offshore wind events. And so we get big fire even without warming. But the warming since 1948 has given us the opportunity to see that warming does have an influence on fuel moisture, at least according to our moisture balance calculations. And so what I showed is that in fall there really hasn't been yet a statistically significant increase in vapor pressure deficit, which is how warming affects fuels. But there has still been an increase. And so, very likely, falls have still been warmer and a little more arid than they would have been without global warming. And so, global warming probably has promoted the ability of these extremely unlucky delayed rains combined with strong winds in fall to create large fires. I know we're in a hurry here, so I'll just finish by saying that like I showed earlier, fires respond to drought exponentially. And so as we move into this increasingly warm world, then the ability of fire to respond to extreme winds and delayed rains will probably increase.
Hey everybody, so a slight change of plan because we're running so late. And we want to give the poster presenters their time. So what we're going to do is we're going to cut the discussion session at the end of this session. It turns out one of our speakers has to leave anyway, which would have already diminished the value of it. So we're going to not have the discussion session at the end of this session, but we will therefore allow a question or two at the end of each talk so that we have at least something. So we'll get through the talks and then with a question or two each, and then we'll go to the posters, hopefully not too much later than the schedule says. So with that, our first speaker, we're very pleased to have, well, first of all, I should say this session is called Sectoral Perspectives on something, I can't remember. Sectoral Perspectives, let's call it that. And societal risk, thanks. And so we're very pleased to have a representative of the private sector and the insurance industry specifically. Steve Bowen from Aon Impact Forecasting in Chicago we're very happy he's able to make it here. I should say that Aon, his employer, is a sponsor of this meeting, which we very much appreciate, and has helped to make it the big event that it is. And so with that, I will be quiet and let Steve tell us about insurance in the era of weather extremes. And I guess this, use that mic? Or?
Either one. Okay, perfect. All right, good afternoon. First, I want to thank Columbia, and I want to thank Bradley and Colin and Adam for the invite to speak here today. And listening to the last day and a half or 2 days of talks, I realized that this might be a bit of an outlier in terms of the type of presentation coming from the insurance industry and more of a private sector view as to how these weather extremes and climate change is having an impact on our industry and sort of how we view these different types of perils and how we utilize the data differently to try to assess and handle the risk that are faced by these big events that occur. So just very briefly, so the typical role of insurance is to create a sense of security, in a sense. You have insurance because you want to feel safe. Insurance is there to protect the interests of its policyholders. But increasingly, the most important component of insurance is being able to manage risk. And we work in an era right now, or live in an era right now, where we continue to see increasing costs from natural disasters. And obviously, there's more concern that these disasters are becoming more impactful from a climate change perspective, and obviously from an exposure perspective as well, which we will get into a little bit later. So in terms of challenges that we face within the insurance industry, it's something called the protection gap. And what this means is it's the differential between what's covered, or the economic cost of a disaster, and what is and isn't covered by insurance. So that's the gap. So what isn't covered by insurance is that gap. So since 1960, there's been $6.4 trillion in economic loss in global natural disasters, in global weather disasters. Now, of that nearly $6.5 trillion in cost, less than $2 trillion has actually been covered by insurance, which means that roughly 1 in 4 of every dollar is covered by the industry. Now, I will say that is highly skewed in the sense that the United States represents roughly 50% of the insured cost. But then you look at a region like Asia, and that percentage is actually less than 10%. So the US has done a much better job in terms of a mature insurance market and having policies in place to ensure that when these disasters occur, people have backup to be able to get on their feet much more quickly. But unfortunately, that's not the case for a lot of other sections of the world. Now, just looking at disaster losses, so here's 3 views of disaster loss. So at the top, you have the nominal economic costs. In the middle, we have the inflation adjusted, so just doing a simple CPI inflation adjustment to today's dollars. And in the bottom here is a normalized view, which is trying to account for current population and exposure and wealth. So when you look at the linear trend analysis, you can see that the top 2 are pretty significant. It's not statistically significant here on the normalized level, but you can definitely see that in all 3 instances, the losses continue to increase. Now, I was asked to give 3 specific examples of different types of events that have been impactful for our industry and also kind of correlate and tie it to extremes in terms of weather and climate and just weather phenomena in general. So what's driving a lot of the big costs? Whoops. That's funky. Okay. So what that's supposed to say is gibberish. I don't know what exactly happened there. Okay, so basically what this I don't know, it's like Coneheads. I don't know if you saw the movie Coneheads. That's kind of what that was. So what this is meant to show is that Hurricane Harvey, so it made landfall as a Cat 5, but most of the loss from the rain aspect of this created Category 5 level flooding. And a big concern of all this is that Harvey caused roughly $125 billion in economic damage, but only $30 billion of that was actually covered by insurance. So a significant portion of this did not actually get covered by private insurance industry. So here's another thing. So this is looking at National Flood Insurance Program policy. So this is looking just prior to landfall. And this heat map here shows where the majority of the active policies in place were. So you see there's a bullseye in Houston, New Orleans, and then parts of Tampa, Miami, Fort Lauderdale, Fort Myers. But when you look at the actual rate of take-up at that time, that bullseye in Houston goes away pretty quickly. So despite the fact that there are a lot of policies there, when you're looking at the actual number of housing units in place that are there, less than 20% of homes actually had an FIP policy in place, which helps explain why there was such a massive gap in terms of what was covered by insurance and what wasn't. So this is a big deal that we're having to deal with, especially when it comes to flood, because whether you know it or not, if you have a standard homeowner's policy, flood is not covered in that. You have to have a separate policy for that to be covered. And the big deal out of all this final gibberish is supposed to be talking about the fact that exposure continues to grow. And Houston is one of the primary centers of this massive exposure growth. So this is a map in 1950 of housing units by county. So let's go to 1980. See a little bit of purple in Houston. Also, I want you to look at Florida as well. 2000, it's red, it's over 1 million. And then where we are today. So you can see there has been quite a bit of substantial growth in Houston. And Houston already is an area that had a lot of concrete, has soil type that is not really able to absorb massive amounts of rainfall. So that water was going to run off anyways. And we're talking about 5 to 6 feet of water. And it really did exacerbate the flood situation. So living in an era where we see these heavier precipitation events in an area that we typically call flash flood alley, from Austin up to Dallas and into Houston, this is increasingly concerning in the fact that we may see more and more of these types of big loss events, but not necessarily big insured loss events, just because of the rain-driven aspect of all this. And staying on the hurricane front, I think it's important to also talk about hurricane landfall risk and the fact that location actually really is a huge driver, and if not the main driver, of losses from these events. So this map here just shows U.S. urban footprints, and I went back and I took the only 10 years of shapefile data from the National Hurricane Center to show the landfalling hurricanes and the associated costs over this 10-year span. And I want you just to look at the different swaths and look at the actual economic costs of these events. And it's interesting because location really does matter from a wind perspective as to what's the primary driver of these events. But you have other events like with Harvey here, $129 billion worth of loss, but it didn't really come ashore near the main, urbanized locations. And that's a bit concerning because we're starting to see these multi-perils within individual types of events becoming increasingly costly. And another aspect, especially with Hurricane Michael, now it got really low. In Florida, for the most part, it's terrible to say, was actually quite lucky in the sense that it hit where it hit. Because if this would have hit Tampa or Miami or closer to Jacksonville, we would have been talking not $25 billion, we would have been talking well beyond $100 billion worth of loss. But a big driver of the Michael cost was actually agricultural, and that's a big deal as well. The same thing with Florence, and also things with like military bases. So some of these different types of exposures that may not be traditionally thought of as being at risk of these events are becoming even more at risk, just as we've seen in the last couple of years. So just something to think about as to how these events are taking place, and the fact that the footprints continue to grow, that's only increasing the risk as well. So wildfire. So there was a presentation earlier which was fantastic, and I thought it tied in quite well to what I was going to present here today. Because wildfire has become, as we know in the last couple of years, a really important component and a very high cost peril, not one that we typically would have considered a primary peril. It's historically been a secondary peril for the insurance industry. So NOAA has a great data set. They have by-county precipitation data going back to 1895. So I just did a simple analysis just to kind of show the rate of growth per county in California. And you can see that there are a few counties in the north where they've actually shown a little bit of rate of growth. But Southern California has actually seen a fairly noticeable decline in precipitation on an annual basis. Now, perhaps even more interesting is I wanted to look at the standard deviation on a decadal basis to show what's going on in terms of rainfall pattern. And you can see every single county is showing a positive growth in the standard deviation, which signifies that we are seeing, as someone mentioned earlier, these faster shifts between years of heightened precipitation to intense drought. And when we're talking about wildfire, that's not a good thing because you're getting this vegetative growth and then quickly dying off, and that fuel sits there, and if it's not properly cleared, you get any sort of ignition, either from utility lines or one of my quote-unquote favorite stories was the Valley Fire in 2015, where someone installed an outdoor jacuzzi, and the first time they turned it on, they didn't wire it right, and it burned 2,000 homes. But this volatility in the rainfall patterns really does make a big difference, and we're seeing more and more of this over time. And going a little bit further in terms of the actual data, I looked at 20-year increments, intervals worth of data, looking at what's typically considered the peak fire months, which would be between May and October, but because the last 2 years the fire seasons have extended into November and December, I decided to include November as well. And it's pretty obvious to see here that in the lower right quadrant, in dry and warm, that in the 21st century, that fills most of the bucket. And when you look at the actual trend line, it is pretty obvious to see that we are trending during these the peak fire season, less precipitation and warmer temperatures as well. And that has led to what we've seen here in terms of most acres burned across the state. This is in chronological order for the biggest acres burned, and you can see that certainly years in the 21st century have primarily near the top of the list. And unfortunately, we continue to see more events like we saw in Paradise, California last year, in the sense that we are seeing massive destruction. And in fact, just within a 15-month stretch, we saw 8 of the top 20 most destructive fires on record in the state, which resulted in a hurricane-level loss, more than $25 billion in insurable loss. So this is a risk that's only going to get bigger. And perhaps the most important component of all this is where we're continuing to build. And this map here is looking at what's called the wildland urban interface and the intermix. The interface is essentially the divide between urbanized areas and more of the rural and brush type aerial coverage, spatial coverage. And then the intermix is actually within the brush itself. And when you overlay the urban footprint, you can see that there's a lot of white that's now being covered by areas that are directly within the intermix and the WUI, and Paradise was directly within the intermix, so it was not entirely surprised that this happened, just given the risk. And just to put some statistics around it, this is using census data. You can see that in these WUI areas, that the growth has been pretty steady, and that is definitely concerning. And just to finally drive home this point just a little bit further, this urban expansion, this is looking at fire perimeters in Southern California in the 21st century, and I want you to focus primarily on the red and the purples, because these are areas that have seen at least 2 fires within the last 19 years. And what's really concerning is that in the gray, which is the urban footprint, that continues to expand, and we are moving into areas that even within this century have had more than 1 fire. And that is certainly concerning because we know fires are occurring, but humans are just kind of saying, I don't care, I'm going to move there anyways because it's prime property. So again, it's increasing risk, and humans have a big part of it. The last extreme I want to focus on is outside the U.S., and that was the big Thai floods in 2011. So here's looking at the footprint. It was a big loss, but the primary focus for the insurance industry was primarily in this red box. So this is where all the industrial estates were that were flooded. So this event was caused by excessive rainfall. You had a sort of an amplified monsoonal season that was enhanced by remnants of tropical cyclones that kept coming in and bringing tremendous rainfall within the fall and into the early winter. But then there was a major human element to all this. In an effort to save Bangkok, they released a lot of water into floodplains, they blew up some dams, and they thought the floodplain was going to be able to handle the volume of water. Turns out it wasn't, and it flooded all these industrial estates, which were all insured, which led to a $17 billion insured loss in today's dollars. Now, believe it or not, that's the costliest insured event on record for the insurance industry anywhere in the world. So that's a big deal. And the fact that it happened in Thailand is an even bigger deal, because it really highlighted the fact that despite being a local event, it had global consequences. And as we live in a more globalized society, supply chain becomes a really important component to all this. And I'm sure you guys remember in 2011, 2012, the cost of your hard drives and external hard drives went up about 200%. And that was directly attributable to the floods in Thailand. So just something to think about, as we live in this era of this more globalization and these big events, weather events having significant impact even on what might be in your pocketbook. So just to wrap up, so insurance and climate change, so it's to be determined. Now insurance, our industry has primarily been based on events in the past affecting pricing for the future. Climate change, as we know, is stuff that happens in the future. So what we aren't quite sure yet how to price going forward, because that entirely changes the business model. And also most insurance contracts are based on an annual basis, an annual occurrence. Climate change is something, as we know, continues over a much longer time scale. So we're not quite there yet, but we're trying to figure it out. And especially as we live in an era of weather extremes and the loss potential is growing, I mentioned the continued growth of exposure. That's only increasing our industry's concern about extreme weather variability and climate impact. And I'll just end by saying that I think collaboration between the public and private sector for risk mitigation is going to become increasingly important. I think conferences like this are fantastic, and because we all sort of work in our own bubbles, so it's kind of good for people to overlap and see what we're all doing. So I think there is a good opportunity for us to start coming up with solutions to try to lower the risk and certainly improve our ability to communicate with people directly so they understand what they're facing. So with that, thank you very much for listening to me today. I'm sorry for being a couple of minutes over. Thank you.
So we'll take a question or two. I think I'm going to take the prerogative, if it's okay with the organizers, and request that we first give an opportunity to students and early career researchers, if there are any who are bold enough to ask a question. If we don't get any after a few seconds, then we'll move on to the old folks. But do I have any takers for that? Yeah. Oh, you got the mic.
Oh, hi. Thanks for the talk. So I just had a thought because I'm working. So I have a colleague who works on flood impacts, and especially the differential impacts in basically poor versus wealthy neighborhoods. And she finds that floods are a gentrifying force. And I was wondering if that sort of if you see among your I don't know how you call that, insurees, how do you call it, a different behavior between different strands of the population that could explain why certain people seem to continue to value coastal amenities despite flood impacts more than another social.
It's a great question. It's a very complex answer. Don't underestimate the power of bureaucracy and power. People want to live where they want to live. If you have the money to do it, no one's going to stop you to build there. And that's a big problem. I actually spoke at a real estate conference in January, and all the developers, not a single person mentioned climate or sea level rise or anything. They're all about, we want the check, we want to build, we want the money. They don't care because the problem is not theirs. The problem is essentially the person that wants to build. Now, the concern is that we are going to start pushing the most vulnerable people into areas that are even more vulnerable from a societal impact, from a loss perspective. There's a great study that was done in 2017 that actually showed with climate change, with every 1 degree Celsius increase, which counties were going to be increasingly at risk from higher damage or greater loss. And the poorest counties in America had the highest rate of impact when we continue to see this growth in temperature and CO2 level rise. So I don't know if I fully answered your question, but there are definitely different societal levels of people that have the means to protect themselves, and that pushes other people away that don't have the means into the really vulnerable spots. And that's something that's going to have to be addressed for sure.
So Should we take one more, or should we
Move on.
What? Colin says move on. Okay. So because we are super duper late. But thank you, Steve. And the next one, let's see, how do I get to the next? I close this, right? And then the next one is the next one. So the next speaker is Jeremy Hess, who's talking about effects on human health.
All right, good afternoon. I want to thank the organizers for the opportunity to come and speak with you today, and thank you for your attention. I'm going to continue on the rightward turn that Steve started. We're going to talk a little bit about cascading impacts in the health system, and I'm going to cover kind of two areas. The first is I'm going to talk some about population vulnerability and an association with population health. And then I'm going to talk with you a bit about health systems and extreme events and how we in healthcare think about and manage extreme events, for better or for worse. And then I'll close with a couple thoughts on how we might do all of this better, including working together to achieve some of our aims. I'm a physician. I'm an emergency medicine physician. I work in a level 1 trauma center in Seattle, Washington. It's in fact the only level 1 trauma center for 5 states. It's a very unusual trauma system in the region. And we deal with a lot of chaos and loss on a pretty regular basis. And one of the things I like about my practice and my colleagues and my community is that we actually are very focused. It sounds a little corny, but we're very focused on determinants of health. And we recognize that health care and what we do has an impact acutely on how people's health goes forward. But there are a lot of other things that matter. And in our region, we know that the environment has a major impact on people's health. And before we send someone back out into the world, we ask have their medical needs been met? Have their other basic needs been met in terms of housing and food and other things? And then does somebody love them? And the answer is most of the time yes, but not always. And increasingly, we're seeing that the answer isn't always yes. And we're having to prop up lots and lots of vulnerable parts of society. Looks like we're also having some issues here. Hopefully this will be the only one. So I was a lead author on the IPCC SREX, and one of the things that we wrestled with as part of that report was the merger of Working Group 1 people, which is you, and Working Group 2 people, which impacts and adaptation, which is me. And we wrestled with the question of where to start. Do we start with climatic hazards and move forward from there, which is, of course, a very commonsensical approach because we know these hazards are harmful. And so why not think about how the hazard is changing and then think about adaptation? But the vulnerability impacts adaptation folks said, no, in fact, what we would prefer is to think about vulnerability first. Because vulnerability is also actually known, and we understand vulnerability as well as we understand hazards. And vulnerability drives risks, and it also drives adaptive capacity. And that's actually really important when you're thinking about putting together adaptation plans, because not all communities have the same level of capacity or needs around what needs to be done. Ultimately, I think it's important to take both of those things into account when we're working on adaptation around climate change and social impacts, including impacts on health. Our chapter actually developed this figure as part of the SREX, and I think it still actually has quite a bit of relevance today, because the question that ultimately we're struggling with here at this conference is, what are the impacts on risk of clustering, particularly in hazards, but also really ultimately in vulnerability and exposure? And Steve's conversation highlighted that, and the impacts on one aspect of risk management, which is insurance, but there are lots of other implications for risk and risk management in addition to insurance that I think we should be thinking about. So a set of questions then flow forth from that framing. And one of these, how do these different risks cluster? And we've heard some about that here. They cluster both in time, they cluster in space, and they cluster in terms of frequency, and that impacts recovery time. They cluster both in terms of hotspots globally, and that may or may not matter, but it often does matter in terms of population concentrations, and then for health people, it matters a lot in terms of the health status of those populations in particular places. And crucially, what kind of vulnerabilities those populations face. What kind of susceptibility do they have to particular hazards when they are exposed to a particular hazard? How much loss do they experience? And then how quickly can they recover? Can they recover at all, in fact? What is their capacity? And that has actually quite a few implications for health. They're, of course, outside of the conventional medical domain, not entirely, but largely. Also has implications for health systems, which are our sort of final line of defense against a lot of these issues when we're injured. And ultimately, it has implications for how we think about these problems and how we work together to develop more effective solutions, because we dearly need to. I think our vulnerability is actually quite high, even in our relatively well-off and protected society. Some of you may have seen this before. It's a framework, it's a qualitative framework around the determinants of health. And there are no numbers here, but I'll put one number up, and that is that healthcare services really only contribute about 10% to the variability in a population's health status. It's all these other things that are really important to developing, maintaining, protecting people's health. And with climate change and these compound hazards that we're thinking about, a lot of these other impacts are at risk. And in a lot of cases, as was mentioned earlier, they're at risk and not necessarily insured. So these losses that we are experiencing aren't necessarily going to be recovered. And over time, particularly as events become more frequent and severe, the limited time for recovery and the lack of resources for recovery means we get depleted, and their communities get depleted, and ultimately that has impacts on health. And I would wager that some of those health impacts will probably be the most substantial that we'll see from climate change. So there are lots of other specific health risks that we could talk about, heat and vector-borne and zoonotic disease and all those other things. I think it's actually those indirect health impacts that will be the most difficult for us collectively. And I would argue we're actually already starting to see it. Solomon Shang and Tama Carlson did some really good work. Starting in 2016, they published work looking at global impacts, particularly on agriculture and nutrition and conflict, all driven by changes in temperature and precipitation over the last several decades. And I recognize that you can't read those specific impacts, but what I want to leave you there with, the impression I want to leave you with here is the breadth, that we actually know these relationships pretty well, and we see them in lots of different domains, and that there's clear overlap in relationships related to vulnerability and compound hazards. And it's not just Sub-Saharan Africa and other parts of the world that we tend to already think of as relatively vulnerable. We see this in the United States. This is additional work that they did with Michael Oppenheimer, one of the organizers of this conference, published in 2017, that looks at the high resource setting of the United States and shows, here you probably can see a little more easily, that there's a real difference in the drop in agricultural yield in certain parts of the country. We see changes related to heat-related mortality, which is going up substantially in the southeast. We see changes related to energy costs going up substantially, again, in the southeast. We see impacts on relatively low-exposed labor. And we see impacts that are quite substantial on high-risk labor, or outdoor labor productivity. We see coastal losses related to damages to property principally. We see increases in property crime, and we see increases in violent crime, both of which are driven principally by temperature. And when you put them all together, you actually see a pretty substantial and somewhat bleak picture, which is loss in terms of county GDP, in some cases up to around 30%. And with our most recent recession in 2008, we had a loss of about 4% nationally. We saw a clear increase in suicides. We saw lots of health impacts that cascaded through our system. And that's going to be paltry compared to some of the losses that we may experience collectively going forward. This is a high emission scenario at the end of the century. The other thing that I want to highlight here is that this loss is not uniform, which is good for us in terms of how we manage it, but challenging in terms of the distribution and how those who actually may gain will deal with losses in cases where people lose. Now, population health is actually not really determined that much by wealth. The United States is a bit of an outlier in terms of our spending on health and the benefit we receive from it. But one of the things that I want to point out to you is that we actually have quite a few different demographics where vulnerability factors overlap, and this leads to substantial differences of about 20 years across these groups in terms of life expectancy. And in public health, we actually use a metric called ICE, which was introduced by a sociologist in 2001, but it's been adopted by some of my colleagues, to look at these compound vulnerabilities. And those of you who've worked with healthcare data know that unit analysis in many cases is quite large. It may be a metropolitan statistical area or a census tract or other things. Health data are scarce and difficult to obtain. But this is something you may think about as you go forward, and you want to look at compound vulnerability, because the vulnerability is just as compound on a social level as it is from a hazard perspective. Impacts on, while I said that healthcare access doesn't drive health, it's still important for health. And we have pretty poor healthcare access here in the United States. Actually, relative to other OECD countries, it's the worst. And this has implications also for population health as a production function. If people can't get access to health, generally their healthcare generally their health is worse. Which leads me to some reflections on the health system. Health systems are complex adaptive systems, meaning that they have multiple interconnected parts that are autonomous. There are emergent, nonlinear dynamics, and the range of emergent behaviors is quite large. Now, our health systems are connected by all of these things here: geography and supply chain, financing, regulation, and importantly, electronic systems. But there's not actually a lot of coordination within different health systems in the United States. That doesn't mean that we don't see significant impacts from relatively small events. And one was Hurricane Maria hit Puerto Rico, and it damaged Baxter's manufacturing facilities, which is where about 70% of our normal saline bags come from, which of course knocked out the supply chain for normal saline. And critically, the normal saline bags that are used to compound medications. And we saw a roughly 20% increase in mortality from bacterial bloodstream infections solely as a result of this impact on the supply chain that cascaded through our whole health system. We also see impacts related to extreme events and lack of coordination between facilities. And Hurricane Sandy here in New York was a great example of that, and several people here lived through that. I'm not going to go through the specific pre-event and event and post-event aspects of the activity, but suffice it to say that it was quite chaotic and unplanned. And we've learned since then that there actually is a lot we can do to better coordinate these activities and leverage our all hazards preparedness. Unfortunately, I work, as I said, in a level 1 trauma center that serves a very large region, about 20% of the population of the United States. We don't implement these recommended rules. We don't implement this guidance, and we don't use these available tools because there's no regulation around this, no encouragement, and we haven't faced the same hazards as they have in other places, so we haven't implemented these protective measures. There's a lot we can do to improve our resilience in healthcare, and one of the things that my colleague Chris Ebi and I have been working on is developing a stress testing framework for thinking about compound hazards, implications for the health system, and integrating this complex systems science approach. And I look forward to questions about this. Thank you for the opportunity to talk with you about it, and look forward to collaboration so we can think these things through. Thank you.
One very fast question because we're a little from early career. Yeah, okay, sure.
Talk out loud. Can you think of any way to model something like that factory being taken out by a hurricane, like identifying important pieces of infrastructure and modeling that extreme weather to impacts?
Yeah, so there's all sorts of different ways that you can look at supply chain. In this case, it was a supply chain issue and constrained supply chain. And then you can basically look at places where those supply chains are constrained and see how diversified you might be able to make that supply chains. But there are lots of different ways. Most of them use system science methodologies to either use agent-based models or systems dynamics modeling to actually capture some of these dynamics as they cascade through the system.
Okay, the ruling is 2 questions. So, anybody have another one? That solves that problem, I guess. No? Okay, yeah, Jane.
Can you describe a little bit more how you're going about this stress testing framework for hospitals?
We've outlined the framework, and then there basically are 2 operational approaches you can take. One is real-time, either through tabletop modeling or, in fact, practice-based exercises, which would be the best. Of course, they're very time-consuming and expensive and potentially disruptive in healthcare systems that are actually pretty much maxed out in terms of capacity, but those would be the best. Other ones are in silico, so you develop some modeling that based on historic patterns in healthcare, and you can see perturbations because the capacity of the system is already pretty constrained. Actually, you can look at little shocks and see how they perpetuate or they cascade through the system, and then assess areas of strain related to staffing and other things, and look at health impacts.
Okay, very good.
Thank you.
The next speaker, I believe, is Jane Baldwin from Princeton, soon to be here.
Still wearing a tiger shirt.
This is the no longer available postdoc position, sorry. How do we, let's see, do that, and Jane is talking about heat waves, I believe, once it comes. Okay.
How do I change this?
I believe it's, yeah.
Okay, great. So good afternoon. Hope everyone's still awake. I'm an atmospheric scientist by training. Unlike Jeremy, who really knows about health, I'm just kind of doing a foray into health because my research began to intersect with it. I'm going to talk about some prior work I've done on temporally compound heat wave events, and then I'm going to discuss some newer work I've been doing to try to more concretely relate our prior results to health impacts, specifically on mortality, which is one of the most dramatic impacts of heat waves. I want to give a quick shout out to Rachel Young, who's a first-year grad student with Michael Oppenheimer, who's been invaluable in helping me understand the statistical models used by epidemiologists and econometrics people in these regards. So go talk to her if you see her. Okay, good. So you all are really familiar with this by now, but a heat wave is a period of threshold exceeding hot days in sequence. And this is a very classic picture of a heat wave. This is a time series of temperature from the Chicago heat wave in 1995. You can see that temperature goes up above this threshold and stays above it for about 4 or 5 days in a row. Now, the interesting thing, though, is if you look at the temporal structure of a bunch of other heat waves that have been associated with high mortality, here we have the 4 heat waves in the Europe and US, respectively, from 1980 to I think maybe 2012 or so, that were associated with the highest mortality. We see there's actually quite variable temporal structure. So in addition to the Chicago and Western Europe kind of classic heat wave structures, which were undeniably really dramatic events, we also see, for example, in Belgium in 1994, this very variable temporal structure where you have temperature going up and down above a threshold many times in a row. And that creates this picture that perhaps many impactful heat waves might be better described as compound in time, meaning that they're composed of these kind of short duration, extremely hot events that occur in sequence. So inspired by this observation, we did some work looking at the hazard from compound heat waves in the present and how it's projected to change with global warming. In the present, we've quantified the number of heat wave days each year that are part of compound events versus kind of all heat wave days. And we find that in the present climate, this is here represented by a control global climate model simulation with 1860 radiative forcing. We find about 10% of heat wave hazard comes from these compound hot days. However, if you look in the future, here represented by a world where we've just cranked up CO2 to twice pre-industrial levels, you can see a significant increase in the proportion of heat wave risk coming from these compound days, which basically says that there is going to be an effective change in the temporal structure of heat waves. If you look at the difference between these two plots, you can see that this increase in proportion occurs across the globe. It's particularly high in the tropics, which is typical of threshold-based heat wave indices. And if you're interested, this work has now been published. You can see our paper to understand why this change occurs and why we think it's robust. But in short, in the present climate, heat waves tend to occur due to systems with some memory, such as a blocking high, versus when we go to the future, you can, to first order, really just think of this time series as being shifted up. So you start seeing heat waves that are composed of these kind of random noise weather variations. And this is really a change in how we need to be thinking about the hazard of heat waves. So we did this work, and as we've discussed many times in this conference, the motivation for studying compound events, it all really comes down to impact. So we wanted to circle back and say, okay, we have this clear result of an increase in compound proportion of heat waves. Does this have implications for policy? And so we started to think about heat wave warning systems. The National Weather Service, one of its functions is it issues these warnings when a heat wave is projected. And how these warning systems work varies from place to place. In New York, just to give an example, you issue a heat advisory if you have 2 days that are 95 to 99 degrees Fahrenheit in the heat index space, where heat index kind of involves temperature and humidity. Or 1 day that's 100 to 104 degrees Fahrenheit, and then you say there's excessive heat if you have 2 hours that are like super, super hot. Again, these numbers vary from place to place, but one thing to take away here is how these heat wave warning systems work, and Jeremy, I'm sure, knows tons more about this than me, but from what I can see, they're almost all based on forecast temperatures. And the interesting thing is in a world where we're seeing an increasing number of compound heat waves, I think a question that's worth asking is, should these heat wave warning systems be considering both forecast and recent past weather? I'm not saying they definitely should, but I think it's worth considering this question as one of the possible implications of this change in compound proportion we see. So what I've been doing recently is trying to dig into this question, and as I've started to look at the epidemiological literature, my view of the different ways that heat waves can compound and the impacts of mortality has changed quite a bit. When I first started working on this question, I thought that if you had a heat wave and as a result mortality increased, then following that heat wave, you'd see some lagged effects from that heat wave that increase vulnerability to latter heat waves. And that this in turn would imply that the mortality of a subsequent heat wave would be higher. There are a few different physical mechanisms you can think about going on here. One is that buildings heat up and they take a while to cool down. There's been well-documented effects in Harlem where they measure temperature in apartments that demonstrate this, that even between two heat waves, I think Michael talked about this a bit, temperature will remain elevated within apartments that don't have AC. You can also think about social system inertia, which kind of speaks to a bit of what Jeremy was talking about. But if you have a really bad heat wave, there's well-documented effects of emergency responders and hospitals and other systems that service people who are dealing with heat stress reaching capacity and as a result not being able to respond as well. So, but as I dug into the epidemiological literature, I also found that there's this other way of thinking about how heat waves might compound, which is that if you have an initial heat wave, the people who are susceptible to die during that heat wave, which is typically the elderly, the sick, individuals who are kind of cut off from other members of society, would decrease because those people have died in the first heat wave. And so then you might see that the mortality of the subsequent heat wave would actually be lower. This is referred to as a harvesting effect or a mortality displacement effect, and it's actually something that's pretty commonly discussed in the epidemiological literature, but it was news to me when I started working on this. And then the third possibility would be something in between these two. So either both of these vulnerability changes and harvesting effects are relatively small, or they kind of balance each other out such that the mortality of the subsequent heat wave would be about the same as the first heat wave. All right, so we spent a while thinking about how we could frame this in terms of a question that we'd really actually be able to dig into. And we ended up landing on this question of, does the sequencing of hot days matter for mortality? And so what we're thinking about here is, let's consider 3 possible Julys. So the first July you have, and let's assume in all these Julys you have only 4 extremely hot days occurring in that month. In the first possible July, you have those 4 hot days occurring one after the other. So it's this kind of classic heat wave structure where you're going up and down above a threshold once. Now, another possible one would be you'd have some short, cooler break in the middle. And then a third possible one would be you have these 4 hot days really kind of spread out in the month. And it's not obvious, first, which month would have the highest total monthly mortality if you're considering both these vulnerability and harvesting effects. It's also not obvious which month would have the single day with the highest mortality. And I would argue that both of these questions are potentially relevant for policy decisions stakeholders would be making. So what I've been doing recently is trying to dig into epidemiological models to try to get at some kind of answer to these questions. And the results I'm going to show are quite preliminary, but hopefully they'll inspire some fruitful discussion. So kind of the state of the art from what I've seen in connecting temperature to mortality is something called distributed lag nonlinear models. And these models are framed basically as follows. You model mortality following a Poisson process, and you relate it to temperature values at different lags, and then you control for various effects such as day of the week, seasonality, trends, et cetera. And what you get out of these models relating daily mortality and temperature effects is a plot that I'm going to show in a second, but basically I'm using some data from Chicago as an example. And I'm going to frame the results I'm going to show in terms of relative risk compared to a 25 degrees C day. And so this is not work I've done. This is a plot I'm taking from a paper. But you can see temperatures on the x-axis here and different lags on the y-axis. So at really hot temperatures, you have higher risk of people dying, and that is lagged for a few days following. And then also at cold temperatures, you have a higher risk of people dying. That also has some lags. We're going to focus on these hotter temperatures today. So these distributed lag nonlinear models can predict mortality from temperature with reasonable accuracy. It's definitely not perfect, but it's better than a lot of other things you could do. So this is a time series from the Chicago heat wave in 1995 again, as an example, and you can see the observed mortality in black and the predicted mortality from one of these models in red. So the general sequence of mortality lines up relatively well with the observed mortality. Here it's an underestimate. If you look at other studies, or other heat waves, sometimes this model overestimates. It just depends on the specific event. So now coming back to how is this relevant for thinking about the compound heat wave events? So one thing you can do with these models is you can separate out what's the effect coming from prior days on mortality versus kind of the day of interest. So here what I'm applying is, again, the observed and predicted mortality from the full model. And then I've isolated, if you're going to just consider the effect of those days prior to like the day and the day directly before, which are currently captured by heat wave warning systems. You can see that a significant amount of mortality during this heat wave is occurring due to temperatures at those greater lags, which is one way in which we might need to be considering temperature from the prior heat wave that might have occurred. And this is just a linear effect, so you're just adding the effects from different hot days in sequence. I'll be done in one sec. So one other question you might ask, though, is whether multiple hot days might have some nonlinear additive effect. And I'm going to have to blaze through this, but suffice it to say there has been some work done on this. It suggests that for heat wave durations above about 4 days, you do start to see some nonlinear additive effects, but it's really hard to disentangle as you go out to longer heat waves just because we don't have that many of them. This is a plot that was created from analyzing 108 communities across the US. There are some bigger data sets that exist now, but this is a fair amount of data that's going into this. I've kind of redone this analysis where I'm considering, well, what if you also add in these compound heat wave days, so hot days separated by short breaks? It doesn't seem like there's any nonlinear addition when you add in these days. Okay, so to conclude, hot days up to 3 to 4 days prior can significantly escalate mortality on a given day. There seems to be little evidence at present that subsequent hot day mortality impacts add more than linearly, but I think based on those linear lagged effects, there's still some justification that heat wave warning systems may increasingly need to be both forward and backward looking in the context of a climate where we're seeing more compound heat waves. And just finally, as atmospheric scientists, it's been really challenging to dig into these epidemiological models, but really interesting. And I'd encourage other people to try to partner with epidemiologists, and because I think there are assumptions that particularly trying to project future mortality, climate scientists might be able to provide insights into what assumptions of these models make sense or don't in the context of a changing climate. So thank you very much. And
Okay, a couple questions. Early career, maybe? Going once? Going twice? Yes, sir.
Do you think there's I'm just sort of speculating off the top of my head, but if the compound nature of a certain heat wave could be amplified in urban areas versus rural areas, just due to the sort of heat capacity of an urban area, you may not have looked at that, but it seems like something logical that could sort of modulate some of these effects, given like population concentration in urban areas.
yeah, that's a great question. So I haven't looked at that specifically. There's definitely a lot of influence that urban heat island effects are really important for what people are actually dealing with on the ground. Most people live in cities. I think there are kind of two levels. It would be interesting to say this further. I'm involved in a project that's looking at kind of if you have an urban tile in global climate models, if you look at the compound heat wave changes in that urban tile versus rural, how that changes. But I think at an even more micro level, it would be interesting to think about what people are experiencing indoors during compound heat wave events. And I think there's still room to do more work in that direction.
I pulled a bunch of air conditioning data recently for energy use, and as recently as that 1980 heat wave you mentioned, only 60% of new dwelling units in the U.S. were built with air conditioning, and now it's about 80-some% or almost 90%. Does the literature show an effect of that in mortality?
I think Jeremy would probably be better to ask about this, but from what I understand, there hasn't been clear influences in heat wave related mortality. If anything, there's been decreases, and it is attributed to there being more air conditioning. So something that I think is worth pointing out about heat waves is they are things we can adapt to pretty well, and there's a fair amount of evidence of that. So it's, in a way, that much more tragic when people do die during heat waves because interventions are relatively simple.
Great. Very good. Thanks, Jane. Okay. And our next speaker, are these in the right? Did 4 disappear? Oh, okay. Yeah, right. Next speaker is Alex Rain, and about correlated extremes for agriculture and food security. Boom. There we go.
All right. Make sure this works. Good. So I'm going to take a little bit of a different approach here and really come at it from the agricultural sector side, and why are we interested in correlated extremes, and where do we stand right now in our ability to actually see this. And I'm going to get into some of the approaches that we're taking, but I would argue that the overall sector is kind of moving into this now, and I'll show you why. So the basic thing I want to talk about is the kind of core types of compound extremes, concurrent extremes, and sequential extremes that we look at in the agricultural sector and that we're worried about, but also get beyond the climate side to talk about how the complex nature of food systems can either exacerbate or buffer or ameliorate the types of shocks that these types of things can cause. Then I'm going to talk about the community of agricultural modelers and things that we're doing to generate and design experiments that allow us to explore extreme responses throughout that whole food system. And then at the end, I'm going to throw a little bit of bonus things on here about some opportunities to contribute in the IPCC and new UN efforts around a global risk assessment framework. Okay, when we're thinking about correlated extremes in the agricultural sector, I want to focus on the fact that this is not just farmland we're talking about. We're talking about the agricultural sector as actually just a small element of the larger food system, which is really the framing that a lot of stakeholders take to this. So this is actually what the food system looks like to a lot of people. This is the cereal aisle in Brazil. At a supermarket, and I noticed they have 3 different types of Frosted Flakes. I have to explore that. But then, of course, there's also the fresh food, and of course, the path to get to these 2 places have gone in very different trajectories and through different processing plants and trucks and ships, and are influenced by a lot of different things. So when we put it all together, the food system is quite complex. We've been talking a lot about the interaction between kind of the climate and the biological system, that is the actual growth of plants and agricultural production. And of course, I would be remiss if I didn't mention that the agriculture is not just plants, it's also livestock and other commodities that come out of that. So there's this side, but of course, before it gets to us, it's going to go through an economic system, packaging, international trade, local markets. Nobody eats international wheat, they eat bread, they eat cereal. It has to get there, it has to be processed. Of course, this is also influenced by the political system, overall consumer demand. And I love in this diagram that the health system is there. To me, it's always just pleading, like, please think of health when the food system is being designed. Of course, this is an important element. But throughout this whole system is the capability of these food system shocks to either explode, or in many cases, there are actors throughout this whole system that can see these things coming and act to increase resilience or respond before things get out of hand. So in that sense, the motivation of why we're speaking about these types of correlated extremes is if we can see them coming, there are actually many, many intervention points in this whole food system that allow us to make something better. When we're talking about food and something as prominent as maize or corn, we have to recognize that this is really not evenly distributed around the world. This is maize production, data from Manfreda et al., around the world, and everywhere you see color, somebody is growing maize, and at least at a fairly substantial level. So maize is a global commodity, it's all over the place. But the global markets don't see this. The global markets see something a little bit more like this, which is the 90% of the, or this is the minimum area you need to produce 90% of all the maize in the world. So you can see a huge number of smallholder and kind of more subsistence farming areas have disappeared, and you're left with very prominent upper US Midwest, a little bit in Argentina. I'm sure in the back of the room you can't even see some of these things. Some of China, some of Southern Europe. But what this does is it sets up a situation where certain areas are much more impactful on the global picture. And therefore, we have to understand what's happening in those places, or if, in some cases, if multiple places are affected at once, that can have really profound impacts. So again, when we're thinking about correlated extremes for food systems, one of the things we're after here is food security. And we have to recognize that this is more than just the availability of food, about how much production we can do, but also access, utility, and the stability of food. It's the expectation that it will be there when it's needed. So we're probably gonna talk a lot about production, but also stability is increasingly worth talking about. And then access is something we haven't talked so much about, but the picture in the bottom right here is when there's a flood, you might cut off the people's ability to get to the markets or the farmed goods to get to shipping and other kind of processing plants. So sometimes it's other elements of the food system that are affected in addition to just the farms. But the core kind of compound extremes you've already heard at this workshop, I want to break it up in this way here, which is that there's the general hot and wet compound problems, which is especially difficult for people who are for animals. So that would be livestock and the people working in the fields. This is a big problem. The wet side is especially important around disease pressure. One of the biggest predictors of plant diseases is whether there is moisture on the leaves. So in these situations where you have prolonged wet spells or wet soils, you can get a lot of disease. The hot and dry side is more prominent around drought and water resource limitations. And then there's the hot and polluted side. I put ozone here, but of course this is also something that can compound and have really dramatic impacts. So there's work in all these areas going on. In terms of concurrent extremes, the buzzword is around multi-breadbasket failures. You're going to hear more about this tomorrow, so I'm going to hold back on that a little bit. And then this example I said where there are situations where there is a crop production loss that might be combined also with lack of ability to get food to the market or to get to the market to buy your food. Sequential extremes are particularly important because the early season characteristics really set the stage for late season productivity. So I threw just a couple examples in here. For example, if there's an early warm spell, you may have a situation where plants are encouraged to emerge from the soil, or the buds on the fruit trees come out and the leaves come out. And then if a frost comes, you can really have dramatic damage. So this is a sequence where the plant is basically tricked into starting its season before it's really safe. And then, of course, there's also other situations where you have an early season wet spell, which may make it difficult to plant and get your machines into the field. And that can push you into the later season, so your maturity now is past the end of the rainy season, and you end up in a situation where the end of year drought gets you, and you need to be able to link that back to that original pressure. When you put this all together, for many decades, going back to 1961 in this graph, this is a food price index, and I'm going to focus on this yellow line. That's the kind of real prices, the prices that people would kind of experience. Going from 1961 or so up towards the turn of the millennium, there was this general downward trend in food prices. And this was the result of the Green Revolution and market efficiencies and refrigeration and all these other things that have really moved forward. But you could probably guess why I've whited out the edge. This turned around, and this suggested that we are actually in a more precarious situation than we had considered, and really challenged this idea that food is getting cheaper at all times. And of course, the spikes that we saw in 2007 and 2010 have been connected to things like droughts in Australia, heat waves and fires in Russia, and other things that have gone on that cause poor production. But it would be impossible to understand these spikes without also looking at other economic effects that tend to also compound these things, such as energy price spikes, declining food stocks, some protective trade policies, biofuel pressures, lots of other things are happening at the same time. And of course, there are consequences in terms of malnourished populations, dietary shifts, the way people budget their food, and many gender outcomes. And in some cases, in those food spikes, we also saw lots of instability in social settings and conflict. And these things are not caused entirely by the food price spikes, but in many cases, they were just one more effect on what was already precarious situations. So what you see here, each of these dashed lines are food riots in different countries, and in parentheses, this was way back in 2011 that somebody tried this, but in parentheses were lives lost associated with those conflicts, and I'm sure if we redid that, we would have different numbers for places like Syria and Yemen and other places that continue to be problematic. So when we put this all together, the agricultural community has come together in something called AgMIP, the Agricultural Model Intercomparison and Improvement Project, which is designed very much to be like CMIP in the climate community, but for agricultural side. So providing some kind of standard systematic approach in how we understand the agricultural systems. The basic model of AgMIP is to couple physical, biophysical, and socioeconomic models in our core framework, to drive it with historical information so we can make sure we understand and calibrate effectively. And then, of course, the really interesting stuff is the future climate and policy scenarios and storylines and narratives that we can pass through that leads to understanding of future and alternative production systems, as well as adaptation and mitigation, many things that we can do. So from this basic model, we now have more than 30 different activities and 1,000 people participating in AgMIP around the world. There's more on here than I can really go through in detail, so I've circled some that are particularly interesting and important. These are all areas where there are multiple groups using multiple models to try to understand problems around seasonal forecasting, pest diseases, ozone. AgGrid is an effort to take agricultural models to the global scale and understand kind of the true spatial patterns for things like multi-breadbasket failures. We do global assessments of markets as well as regional household-based systems. And we even go to very fundamental level to understand how crop and evapotranspiration, or how crop water and evapotranspiration are acting on fields in response to these extremes. The way a crop model actually works is digitally growing on a daily time step a plant with inputs from or information about crop management and many climate factors. But this allows, a process-based model really allows impacts to compound and to build up over time. So you can see those effects in the early season having ramifications later. We've designed the approach to look both backwards in historical kind of retrospective analysis, so we can do detection and attribution as well as counterfactuals to see what we could have done better. There are many factors we're looking at in real time or forecast mode. And then the long-term outlook, of course, changes with things like climate change and socioeconomic development. One design that we've put together in our gridded models and a couple other approaches is to avoid specific scenarios and just explore the climate change space. So we've run our global models with various carbon dioxide levels, temperatures, changes in precipitation, nitrogen levels, and some basic adaptations. And this, in individual but also in combination, allows us to build response surfaces that help us understand how the average yields will respond under these various climate conditions. But it also allows us to go and look at individual years that are happening. So one last thing I wanted to show is we can go back and look at something like the 1988 drought, which is very famous in the United States, a big agricultural production loss. But you'll note it also corresponded with some losses in Argentina and southern South America. And we can go back and we can look at that same year and ask ourselves, what would it have looked like if it was a degree warmer or a degree colder? And likewise, what if it was 10% wetter and 10% drier? And this is every grid box in the world has these effects. But what I wanted to point out is even if we just make it 1 degree warmer, Northeast Asia, some of these big breadbaskets also become a third failure. And this starts to suggest that some of these changing background conditions are leading to these correlated extremes. I'm going to skip this, but you can see lots and lots of different examples we can look at. And then I'm going to finally end with just a plug. The IPCC has a new focus in the 6th assessment report. There are several lead authors here in the room. And I think everybody should know that we are interested in submissions by the end of this year. Lots of what we've seen in this workshop would be relevant. In particular, Chapter 11 is on climate extremes, and Chapter 12 is translating this information into some kind of practical use for various sectors. I also wanted to just mention that the UN Disaster Risk and Resilience Office has a global assessment report that has just come out a couple weeks ago called the GAR. And that's something you can find online. It gives you a whole kind of disasters and risk transfer perspective on the types of things we've been talking about here. So I'll leave up my summary, and thank you for your time.
Okay, thanks, Alex. Questions from early career people? Once, twice, from anybody? There we go. Yes, sir.
One of the questions that I've got is around micronutrients and micronutrient incorporation into the plant and then staple foods, and how likely it is to ultimately affect people's diets and health. And I wonder if you have insights into that.
Yeah. So the question was if micronutrients, so the nutritional content of foods, is taken into account. So there are climate change implications. Carbon dioxide itself can change the nutritional content of many things. But I would say for this group also, drought and other heat events can also have effects. And for many crops, we're worried more about quality than quantity. So this is something that we're factoring in both in our dietary design and in our overall projections.
One more?
Maybe while she's getting the microphone, I should also add that there's evidence that the alcohol content of wine goes up with climate change. So maybe people like that.
So I was just curious about the design of AgMep. Does it include the effect of aerosols, like in the historical simulations? Does it include aerosol forcing or other pollutants other than, like, ozone is just produced within the system, right?
So we are driven by the climate information, so the aerosols are there, but for the most part, the crop models don't have a very strong response. So we have people who are working on air pollution and ozone impacts, and in some parts of the world, we know that that's a big signal. But I would say at this point, we're still trying to add that response. We have a team working on that.
Okay, thank you. All right. Next up is, I have to look at the slide to get the speaker's first name, I'm sorry. Lisa Thalheimer. Is Lisa here? Yes, she's coming. Okay. Displacement and conflict. No? What'd I do wrong? Oh, that's wrong? I thought that was, but what if this is 5 and this is 6? That's wrong? Okay. I was just reading the numbers. Sorry. Weston Anderson.
Great. So I'm going to be following on from what Alex was just talking about and talk more about one specific piece of food security, namely, he alluded to it, what could cause multiple crop failures. And by concurrent crop failures, what I'm talking about is crop failures in distinct agricultural regions that fail in the same year or simultaneously. This is all work that I've done with Richard Seeger, Walter Baithkin, Mark Kane, and Liang C. Yu. Now, there's been an explosion of interest and research on this recently, much of it done by folks in this room, and with good reason, because our global food production system, as Alex mentioned, is just that. It's global. It depends on pooling risk in a way that if you have crop failures in one major producing region, you make up for that with production elsewhere. So much of this work has focused on what's the probability of multiple crop failures, both in the present climate and in the future. But if we're going to monitor these events, if we're going to predict them, if we're going to better understand them, we really need to know what's causing these crop failures. And there are two sorts of bins of hypotheses that you could come up with. You can either say, well, perhaps it's just random chance, essentially bad luck. Multiple crop failures in two regions from random weather. Alternatively, there could be a global scale forcing. We've heard one hypothesis already from earlier presentations about these either global scale or regional Rossby wave trains that could set up forcing patterns. But I want to talk a little about another possibility, which is the El Niño Southern Oscillation. As Radley alluded to in his introduction, we already know that ENSO organizes climate at a global scale. And since, at least the early 80s, there's been a lot of literature that demonstrates that during strong El Niños, you stabilize your tropical troposphere, you increase the probability of drought throughout the tropics. And so right there you have reason to believe that you're organizing the regions in which you're going to get crop failures. In addition to this tropical mechanism, you likely incite this deep convection in the tropics will force Rossby waves that propagate into the mid-latitude, so you have a truly global organization of climate, which may imprint on agriculture, but not necessarily. So what we wanted to do is we wanted to look through to say, okay, well, what are agriculturally relevant teleconnections from ENSO, and how might they imprint onto global agricultural regions? So to do that, what we're going to do is we're going to look at identifying the growing regions, growing seasons. We're going to look at heat and moisture stress in observations, and we're going to compare that to multi-model ensemble averages that try to separate out what's the forced response of heat and moisture stress and what is sort of noise in this small observational composite. So we're not just going to look at maximum temperature and precipitation. As we've heard already in this conference, it's important to look from an impacts perspective. So we're looking at killing degree days, which is essentially the number of days that produce damaging temperatures to crop yields, which is above, for maize, this is in the range of 30 degrees, and soil water content, which reflects the ability of a plant to access water in the soil in addition to just soil moisture anomalies. To isolate the effects from ENSO, we're going to look at AMIT multi-model ensemble means to dampen out atmospheric variability and try to isolate what is a response to sea surface temperature forcing. So here on the left, we have observations. On the right, we have this AMIT multi-model ensemble. In this top row, this is moisture stress. The bottom row is heat stress. And this is only for during La Nina, during local maize flowering season. So this will be boreal summer in the northern hemisphere, boreal winter in the southern hemisphere. Now, the takeaway from this is really that the observations do look remarkably like the AMIT multi-model ensemble mean, so this is a forced response to boundary conditions, and that there is a pattern imprinted from this La Nina into growing regions during the flowering seasons where you get increased heat and drought stress in some of these major bread baskets. So in the US, in Southeast South America, the good growing conditions may be a little harder to see, but they're in China, in southern Mexico, in the Cerrado or parts of Brazil. So there's this real structure, this organization. It doesn't cause drought everywhere, but it semi-predictably organizes the regions and the timing of the drought and the heat stress that we do get. So we can ask, okay, what's causing this? We can go back to our large-scale circulations. Here I'm showing 500 hectopascal geopotential height anomalies, and I'm going to focus on these, what we call trans-Pacific anomalies or wave trains, because these are anomalies that are connecting major bread baskets. So the US and China, depending on your crop, Southeast South America and Australia. We can look not just at geopotential height anomalies, but at anomalous ascent shown in blue or descent shown in red, which is important because if you have ascent in your air column provided with a moisture source, you're likely to have precipitation and relatively good moisture conditions for growing maize. This is largely consistent just with vorticity balance, so you're balancing convection of planetary vorticity with vortex stretching or compression. And that's really just to say that this may be new in the framework of multiple breadbasket failures, but these are dynamics that we understand on the large scale and can be reproduced from models. And this leads and is consistent with these large scale dynamics are consistent with the patterns of heat and moisture stress that we see in growing regions during growing times. Now, all of that is stress, potential impacts, but it doesn't say, do we actually see an effect on the yields? So to get at whether we actually have impacts on crop yields from these ENSO events, we're going to switch and look at observational statistics, often subnational statistics that we compiled, and we're going to do a maximum covariance analysis between climate variables and crop yields. And what this will do is it'll allow us to isolate the portions of the yield variability that's forced by climate indices or climate events. So we want to focus specifically on these bad events, and the one that we're going to choose to isolate is 1983, which is one of the largest concurrent crop failures in the modern historical record. So when we look at 1983, just look at the observations to say, what are the maize yield anomalies in 1983? You have poor production in the US, in Northeast Brazil, West Africa, Southeast Africa, good production in Eastern Africa, India, and parts of China. Now, if you know, 1983 is also one of the largest El Nino events at the beginning of the calendar year in at least the last 150 years. So this is a Hoffmöller diagram starting in January at the top, time running down to December in the Nino 3-4 region. So this is showing that by the end of the calendar year, we've transitioned into a La Nina event. So now we can go back to our maximum correlation analysis to isolate how much of this is attributable to this ENSO event. And there's a remarkable correspondence between the observed yield anomalies and the ENSO force anomalies. If not in magnitude everywhere in the US, for example, this could either be nonlinearities or other factors, because this is a linear analysis. But virtually this entire pattern is what we would expect from strong ENSO forcing. A valid criticism is, well, it's getting cut off, but this is just a statistical analysis. So perhaps this is baked into the tools we're using. How do we know whether this squares with the dynamics that we understand? There's a vast literature that we can compare with. So that's what we can do. We can go to each of these regions and say, during this crop flowering period, how does this compare with observed and understood connections between El Nino and dynamics and El Nino and crop yields? So we know that strong El Ninos tend to bring more moisture into southeastern South America. This leads to good maize growing conditions, whereas southeastern Africa, it forces drought, which would force crop failures. We know from that stabilization mechanism, as well as a number of others, that you force drought in northeast Brazil and West Africa, although these could be modulated by the tropical Atlantic. And in the northern hemisphere also, while some of the literature is a little more scarce, particularly in areas like the US, summertime, but all of these observed impacts are consistent with the ENSO teleconnection dynamics that we know and with the statistical analyses between ENSO and crop yield anomalies. So this is just to say that we do believe that ENSO can force multiple crop failures and may organize crop yield anomalies in a real way at a global scale, not just in a composite mean, but in individual events. So ENSO may not drive all of the crop yield anomalies. We did, in addition to the single event, we tried to estimate the total variance that it accounted for over this time period. And at a global scale, it's really only accounting for maybe 10 to 20% of production variance, but it might be playing a particular role in these large multi-breadbasket failure events. So the point of this talk is really just to say that we've known for a long time that ENSO can organize climate, and that we should start to consider from an impacts perspective what that means for crop yield anomalies. This is very likely not the only thing that could cause multiple breadbasket failures, but we believe that it's one of the potential causes, and if we're going to understand why these events occur both in the present climate and in the future, we should understand what drives them. All of this is taken from two publications, one that's been accepted and will be published sometime in the summer in July, and one that's already published in Agriculture and Forest Meteorology. So I'll take any questions.
Yes, sir.
So one area of sort of active research right now with ENSO is looking at this difference between Central Pacific-based ENSOs and East Pacific-based ENSOs, and we know there's a large difference in the extratropics, in the extratropical response between those two kinds of El Niños. And so I was wondering if using, breaking it down further into two separate types of El Niños would enhance your statistical sort of response?
I think if we had the data available to do that, it would certainly enhance our understanding, because you're absolutely right that there are known differences in some of them in these agricultural areas. The difficulty is we have a short enough data record that you can't, just statistically, the first two modes that make up our maximum covariance analysis that I showed here are separable. Beyond that, they're not. So it's unlikely that we have enough statistical data to answer that question. Right now, we're only using 1980 to 2010 so that we can use subnational statistics. If you went back to 1960, you could use national statistics, but you're likely to lose a lot of your the power in the analysis by moving from subnational to national in countries like India, China, Southeast South America.
For India, you showed that in INSO your crop yield is increased, but normally when INSO is happened, there is less rainfall in India. Second, in your crop yield mainly not only depend on precipitation but also groundwater, but groundwater not depend on any INSO condition. So crop yield is bias, if you can say bias indicator of in climatic factor.
Yeah, absolutely. So for first the irrigation question, if you look at the effects of ENSO on wheat yields, particularly because of the heavy irrigation in both India and the North China Plain, you see a very dampened response. And that likely is modifying the vulnerability rather than the hazard. So we know that there's a teleconnection to India during the wheat growing season, but it's doesn't show the magnitude of the response that you might expect because of the heavy irrigation with groundwater. For El Niños causing crop failures, this is where it's important to consider how the seasonality of ENSO event developments and decays with the growing season, because although 1983 started as an exceptionally strong El Niño, by the time we entered the Indian monsoon, so by the time we entered into boreal summer, it was a La Nina event. So there's a mismatch where El Niños tend to peak in boreal winter, and so the summertime crops in these growing conditions are often affected by either the developing or the decaying phase of ENSO. And so in this particular event, why I'm showing it in blue there is that the growing season, this is for maize, occurred during what was by that time a La Nina.
Okay, thanks, Winston. So now, actually have our next speaker, Lisa Thalheimer. Thank you for your patience with our technical difficulties. Speaking about displacement and conflict.
Good afternoon, everyone. My name is Lisa Thalheimer. I'm a second-year PhD student at the Environmental Change Institute in Oxford. It's actually a great pleasure to be back at Columbia, which I'm fortunate enough to call my alma mater. And yeah, many thanks to Colin and Bradley for inviting me and giving me the opportunity to give a presentation, though I was slightly late with my submission. So thanks for that. And I would also like to thank the Earth Institute staff for really making this a wonderful event, as well as the organizers. So today I would like to talk about kind of complex systems of conflict, extreme weather, and displacement. This is a country case study of Somalia, which you can see kind of on this like blue dot. Somalia is a country in East Africa. And it's been really interesting over the last couple of years determining the role of climatic change. So independent of the causes, such as, for instance, anthropogenic climate change, in times of drought, if that leads to armed conflict or not. And there's an extensive academic literature out there which looks at these different dynamics. However, there has not been a lot done on the quantification and disentangling part of that, especially in recent extreme events. And I prepared a little animation of displacement across Somalia, and you will see two distinct colors, blue and orange. Orange relating to drought-related displacement, and blue is I picked for conflict-related displacement, just to have two contrasting colors. And I would like you to focus for a second on. Is it? Ah, there we go. No. Oh boy. Do you see it? Okay, great, fantastic. For a second on the different colors and where across Somalia we see the different colors occurring, whilst I give you a little bit of more background information. A study has been published earlier this year by Guy Abel and colleagues, and it finds that most of the literature is organized along a triplet axis of climate change and migration for once, and then climate change and conflict, and then conflict and migration. And this is really difficult to disentangle all these different drivers. And in East Africa, where you have migration as something people do that on an everyday basis, it's really something substantial to look at extreme weather events and how existing migration patterns change. This has been covered by the media quite a lot, I would say. A global debate has emerged whether the human impact of climatic change can lead to armed conflict, and how conflict and extreme climate events interact and potentially even induce large-scale displacement. Oh, there we go. I don't see it on my screen, but you see it immediately on this one, so there is kind of a lag effect here. So what I found really interesting over the last month and I would say 2016 to nowadays, we see a lot of new articles from the New York Times, The Economist, which you see in the middle, and The Guardian as well. So really big newspapers covering this topic, but also kind of portraying a quote-unquote doomsday scenario. So if you look at the middle picture, how climate change can fuel wars doesn't sound very positive, does it, right? And if you think this is only something occurring in places far away, like small island states or even countries which are, characterized by poverty and conflict, that's not true. Because now I see it on my screen, but you don't see it on. Well, all right, there we go. In Britain, The Guardian published an article earlier this month which links kind of this topic of climate refugees to communities within the UK. So you see that also rich countries like the UK and Europe are affected, or could potentially, even with climate change, be affected by that even more. But as I find throughout my research, everything is a bit messy, if not to say chaotic. So as the mathematician Alfred North Whitehead famously said, the only simplicity to be trusted is the simplicity on the far side of complexity. Great quote I found. If you look at the modeling approach, which has been done thus far, I found that Black and colleagues really captured the different drivers surrounding migration in this kind of chart very well. So it's important to note that migration is not only driven by one factor, it's definitely multi-causal. It has many influences which change over time, over geographies. And this graph really nicely shows the different non-environmental factors, which I refer to in my presentation here as contextual drivers. So we see on the top the social factors such as education, social norms. We see demographic factors, urbanization, population growth. We also see economic factors, economic opportunities. You might migrate to an urban area, for instance, because you have a better job offer there, you get more money, something like that. Or political factors, political stability, conflict, are things which really impact people's decision whether or not to migrate. In my talk, we're going to focus on the decision to migrate, and here we have a differentiation between cross-border, which would often be referred to as international migration, or internal migration, which would be within the country. And we're going to focus on the internal migration within Somalia. So diving right into the context of Somalia, anthropogenic climate change will hit the world's poorest first and hardest, and nowhere is that potentially truer than in Somalia, which is a scattered consortium of the Southern Federal Republic of the Federal Republic of Somalia and two kind of semi-autonomous states, which are Puntland and Somaliland. And this all is located in the Horn of Africa, where there's a lot of interesting climatology in general going on. And in the context of Somalia's factors which are essentially of particular concern reach from conflict. You have the militant group Al-Shabaab there. You have a lot of poverty going on. You have limited presence and capacities of government institutions overall. You have the lack of basic services, basic health facilities, unfortunately. So there's a lot going on, a lot of unfortunate complexities. And within the year 2017, Somalia was hit by drought events, and more than half of the Somali population was in need of humanitarian assistance throughout the whole country. Okay, fantastic. So we started our modeling approach with a more qualitative overview in order to get a sense of what has been going on in the country, where there's so much complex things going on. And this graph shows a timeline of agricultural output and climate conflicts, as I would refer to. So on the x-axis, you see the time from 1980 to 2017, and on the y-axis, you see the production index. This is data from the World Bank. So in dark gray, crop production, and livestock production in light gray over this time frame, the time series. And there are two main things we can kind of learn, or I would like to point out from this graph. Okay, fantastic, that's working as well. One is that agriculture, which represents the backbone of the Somali economy, is more or less stable despite recurrent economic and climate shocks. So if you look over the time series, it's more or less stable. However, during the time of 1991, where you had the Bar government, which was overthrown, and civil war, which was kind of 3 years before that, it had a very big impact on it. And the war, together with the putsch, had this significant impact on agriculture. And also prolonged El Nino conditions kind of contributed to this whole crisis. And the other thing we can learn is when we look at the bubble on the very right. So during 2011 and 12, there was the big East African drought series, and you can see a big impact on agriculture as well. But it's also interesting that if you look at the livestock production in light gray, see that this kind of actually benefited from the drought conditions, which is really interesting to note. And just to summarize again, we see the characteristics of a war economy, which is more or less very resilient to external shocks, both in this case in Somalia, climate conditions and conflict conditions over time. We see also that contextual drivers contribute to the frequency and intensity of the crisis across and in Somalia. Next, I would like to dive a bit more deeper into 2017, essentially where the last graph ended. During 2017, there was the Somalia drought, and I believe the conditions are unfortunately still ongoing, the drought conditions. So here we see a map of precipitation anomalies from the TURPS data set during the onset of the ongoing drought, October 2016 on the left, averaged over 4 months. And the same for the time in October 2017 on the right. But we still don't really know what's going on with displacement. So, there we go. UNHCR actually collects data on the ground in Somalia and categorizes why people think they have been displaced. So people get interviewed at certain checkpoints within Somalia, and they list their number one reason why they claim to have been displaced. This is categorized in flood-related, drought-related, and conflict-related. And here we can see on the top drought-related displacement during 2016 to 18 and conflict-related displacement in the same time frame. And there are two things which I would like to point out here. So Banadir, which kind of is the region which relates to the star, Mogadishu, which is the capital of Somalia, has very interesting dynamics. We see in the time of February 2016 to July 2017 that there was major drought-related displacement in the area of Mogadishu, so in that urban area. And what's interesting to note is, if I get that pointer to work, oh, fantastic, that a couple of months later, we see that the drought-related displacement actually turns into conflict-related displacement. So there are interesting dynamics going on. But we still are not there yet, right? We haven't quantified it yet. So how do we go about disentangling and quantifying climate and conflict-related drivers of displacement? So we estimate the impacts of climatic change from observed rainfall and temperature on in-country displacement and conflict events using econometric methods, in this case, a panel of monthly regional level observations. And we have two assumptions I would like to note. For one, we assume that the internally displaced people actually report truthfully that their primary reason has been drought, flood, or conflict. And we also assume that out-movement does not necessarily cause conflict, right? This is an overwhelming graph, I admit it, but I thought it's useful to just show you an overview of what we wrap our head around. So we came up with preliminary identification strategies, and we considered 5 channels of potential effect. Due to time reasons, I do limit myself and dive right into A, which is we look into rainfall and displacement relationships. Oh, fantastic. Oh, is this cut off? I'm sorry. So the relationship between rainfall and displacement is nonlinear, as we find. We plotted the CHIRP's mean rainfall across Somalia across the time series, and have 2 major observations. For one is that when you have very little rainfall, a lot of people get displaced. There's a certain threshold then again, and when you have a lot of rainfall, people get displaced again. But there's kind of like this sweet spot in the middle where you have like around 100 to 150 millimeters per month where there's barely any displacement at all. So some potential channels and effects. So first, the rainfall and displacement channel is more straightforward. If we look at the conflict channel, it's actually not that straightforward, and it still remains kind of the X factor. So we again need to wrap our head around that and try to see if conflict actually has anything to do with climate and displacement or not at all. So findings in plain language. In Somalia, displacement is multi-causal, as I pointed out, and it cannot actually be seen without the historical and economic interlinks. When you look at conflict, it's very dynamic and very complex. You have a lot of different actors, from Al-Shabaab to the army there to the US who intervenes, so there's a lot going on, essentially. And conflict appears less of a driver of large-scale displacement, rather representing a constant feature. If you remember the kind of heat map I showed, it's conflict is always essentially there, unfortunately. For the displacement data, and that's kind of common in migration studies, you have data scarcity, obviously. So this data set is really nice and neat, but we only have 3+ years of data. However, and then this is kind of my perspective, I think this research is really relevant for policymakers and humanitarian aid agencies if you want to deliver the humanitarian aid on the ground and really want to see where it should be targeted at within the country, and also if you think about cascading impacts for the broader region. And then there's ongoing research with Alison Haslund here from the Earth Institute, where we recently wrote a paper which is now under review concerning addressing root causes of displacement, and we think that satellite data offers an opportunity to supplement ground level data collection for targeted intervention in areas where you actually have these like displacement hotspots. So that could be something really interesting to come in with new types of data and see if you can have people on the ground real time. My references are here. I do have a Twitter account and a GitHub as well. And I have an email, so if you have questions, please feel free to ask. Thank you.
Okay, early career questions first, if we have any. Going 1, 2, okay, any questions? Yes, sir.
I wonder if you can distinguish the people who are displaced for drought. Is it the farmers themselves or people who are dealing with the drought's wider impacts?
So the thing we see is we see the bulk of people who move. We have data on origin and destination, but unfortunately there's not that granular data that you see, the age, the occupation. That's not, I assume that UNHCR collects and has this data, but they don't make it public as far. But it's a good question.
Anyone else? Yes.
What's your hunch as to the generalizability of some of the dynamics that you observed in Somalia, particularly potentially related to Syria or some other places where similar theories have been postulated?
I think since this is a very hyped topic and very political, I would not generalize anything at all. Maybe if you look at a global scale, yes, and especially if you have a longer range of data. We have 3 years of data, essentially. UNHCR data, it goes back to 2007, but it's a bit, they changed their methodology and so on and so forth, so it's a bit, yeah. I would not go with any generalization for Somalia with this type of data we have so far.
Okay, thanks very much, Lisa. So I think the next one is the last one of the session. If I can change here. And it's James Stone from NCAR. And he's talking about flood risk and water resource management.
Okay, well, yeah, thanks everyone for sticking around. I'll make this short and punchy. So yeah, I'm Jim Stone from the National Center for Atmospheric Research, and I'd like to present some results of some interviews we conducted with water managers in California to learn about their vulnerabilities to correlated extremes. So thanks to my NCAR colleague Erin Towler, who's here in this room, and thanks to my NCAR and UCLA colleagues here. Okay, a quick summary then. So I'm going to identify some vulnerabilities to correlated extremes for flood risk managers and water managers. Then I'm going to present the finding that water managers actually want us to understand causality of correlated extremes. And then I'm going to take this understanding of societal information needs to motivate a new project that we have where we're framing extremes as connected. So connectedness is a fundamental property of all extremes. Okay, so these interviews were conducted as part of a broader project aiming to understand the role of actually decadal climate predictions for water resource management. But the actual results were primarily mapped onto correlated extremes, and that's why I wanted to present it here. So this was a large 5-year project that I led called UDecide, so understanding decision climate interactions on decadal scales. So it involved physical and social scientists from NCAR, statisticians from CSU, policy and risk perception experts from Wharton, and engineering consultants who design for climate change, Jacobs. So let me know if you want to hear about more aspects of that project. So just by way of motivation, so what's the potential value of decadal prediction? Well, I'm just going to illustrate it here. So when we think about climate change, we usually think about some delta that we could linearly extrapolate in time. So on the y-axis here, we have some climate impact. It could be flood height, for example, or drought duration. So a climate change projection, we think of some linear interpolation. Whereas a decadal prediction, it tells you something about the climate variability, so the time-varying trajectory of how we get to this future. So in this case, a lot of the change happens in the early period and not much change in the later period. So if you're a flood water manager who has some decision that's relevant on this timescale that's shaded here, whether you look at the prediction or the projection, you get a very different answer. So that's the potential value we're interested in this project. The data set we're using is the Decadal Prediction Large Ensemble data set. So this was recently generated using NCAR's Global Climate Model, the Community Earth System model. The data set we're using is the prediction that was initialized in 2015, and it goes out 10 years. So it's not just one projection, it's actually a 40-member ensemble, so we have 40 futures. And just to note that we did drift correct, so we removed this lead time dependent bias that's inherent to these data sets. So Steve Yeager, who wrote the summary BAMS paper, noted that this data set was good to identify shifts in the extremes, but I'm going to argue that it's also a great data set to understand correlated extremes. So back to these interviews then. So we wanted to understand the role of decadal climate prediction for water managers, and the way we did that, we basically presented different plots of decadal prediction and asked them questions and tried to understand how each one was useful. So today I'm just going to show you one of those plots, and it's going to be for data integrated over the area of the Sacramento River Valley, which is the blue shading here. So this is the one plot I'd like to show you. It's a bivariate prediction of annual temperature anomaly versus annual precipitation anomaly compared to the 1981 to 2010 average. Each black dot here is an historical year, and the red diamonds are predicted years from 2015 to 2024. Each diamond is a different year, and each diamond is the ensemble median. Now, the grey ellipse is the 95% confidence of each individual ensemble member. So we've got 40 members, 10 years, there's 400 data points that inform that ellipse. So we showed this to the water managers, and they were immediately alarmed by the big lobe of predictability out here. So this is unprecedented, or in their words, it's beyond their operational space, their operational climate. These very warm and very wet years that they've had no experience of. So this is a very large flood risk for their management strategies. So like I say, I'm just going to show you this one plot and then just summarize the other vulnerabilities that we identified through other plots. So I'm going to use the categories of the three different categories of the correlated extremes that were identified in this workshop. So first, the compound extremes that I just showed you the plot for. So flood risk, but also water supply is very vulnerable to these bivariate temperature and precipitation extremes. So the needed science then is we need to understand the mechanisms and predictability for these seasonal bivariate extremes. And throughout the past couple of days, we've seen a lot of work going in this direction. In the category of concurrent extremes, the entire state water supply is extremely vulnerable to multi-basin, multi-year drought. So the needed science then is to understand, what connects extreme dry conditions in space and time. And again, we've seen a couple of talks exploring this kind of question. And finally, in the category of sequential extremes, we identified that some drinking water supply is very vulnerable to heavy rains on burn scars. So they're very vulnerable to back-to-back extreme dry followed by an extreme wet year. So the heavy rains on the burn scars washes the sediment into the water supply. And then we just heard earlier today that the actual wildfire is also very sensitive to these back-to-back or these whiplash events. So there's a number of nuances of how this increase in volatility drives impacts and vulnerabilities to correlated extremes. Okay, we're just talking more generally then about what we learned that water managers want to know. The very savvy users of climate data, if they see an extreme wet year in a prediction, they're not going to do anything, or at least the people we talk to, they're not going to react, but they use it for what they call situational awareness. So if there was a signpost, in their language, in the Earth system that pointed towards this extreme wet year happening, then they might start to react. So if we know something about, say, SST spatial patterns that correlate with an extreme wet year, then they might start to act. They want to know that, as climate scientists in the room, understand causality for correlated extremes. So this is great motivation then for us to indulge in basic science, guilt-free. And they also want to, this last one was quite interesting, they want to know how soon conditions will return to normal. So do we know after a correlated extreme that we will actually fall back to normal operational climate? They actually like to be tested for, say, just 1 year to test out new management strategies, safe in the knowledge that they can pick up the pieces the next year. Okay, so we've taken some of that knowledge of information needs to inform a new project that we call Coexist. So the acronym is Connected Extremes in Space and Time. So apologies for introducing yet another term to define correlated extremes, but with connected extremes I mean it's something that we understand the physical process that connects them and makes them group more than they would than random chance. So this is a NSF-funded 3-year project, so I'm leading a team of physical scientists with NCAR, UCLA, and UCSB. So the whole point of the project then is to frame all extremes as fundamentally connected, and using that frame to advance our understanding of extremes in general and predictability sources. So why are we doing that? But even after 2 days of talks, I think we still have a lot to understand about the processes that connect extremes. Are they unique in each case, or are they shared? Is there a fundamental shared process? And also, I haven't seen much in the way of predictive capacity for correlated extremes. So there's a lot to learn about what's our subseasonal to seasonal predictive capacity. So let me just summarize our approach in this project. So it's just getting started next month. So we've taken our societal information needs to inform this project, and to make progress, we're just looking at precipitation extremes, wet and dry extremes. We're going to start by conducting a multi-scale observational analysis of surface station observations across the United States, apply statistical modeling to quantify the degrees of connectedness, interact that with various environmental parameters to develop hypotheses about the connecting processes. So of course this will vary across the United States. And then on the right-hand side, we're going to conduct multi-scale modeling to understand and advance these hypotheses, and then take that understanding and test out prototype forecast systems to understand if we emphasize these connecting processes in forecast systems, does that expand our predictive horizon for these events? Okay, well, I'll just summarize then. So identified various vulnerabilities of water resource managers to correlated extremes. We have this golden motivation here to do basic research. The water managers need this information to be credible. We need to understand why these events happen. And then I articulated a new project that's just underway where we're framing extremes as fundamentally connected systems. And just to be consistent with other projects, we have a graduate student opportunity on that project, so tell your friends and family. Thank you.
I have a couple questions. An early career one. That one. Or whoever, I guess. Nobody speaks up. Quick. No questions for James? Everybody's worn out? Yes, Jiaying.
So how do you think of can you talk about your idea of connecting the extreme, like in your last project, how you think of connecting the extreme, like heat, temperature, and the precipitation in the different locations? Because you are thinking of like physical process connecting all, so they're not always necessary on the same spatial location, location.
Yes, so we're going to develop metrics that quantify the degree of connectedness using statistical analysis, and then interact that with environmental data. So over the western US, it's likely to be atmospheric rivers. Over the central US, we're thinking MCSs. Eastern US, there's probably a TC signal. So, and then we're going to conduct multi-scale analysis. So what are the large-scale states that encourage those synoptic-scale weather systems to group in time. We heard a lot of mechanisms already over the past 2 days, so there's going to be lots of exciting processes to explore. Thanks.
So in your ensemble modeling, was it consistent that you found warm and wet for California? I thought there was some predictions that it was going to dry out across Cal, maybe with the jet displaced northward, or
yeah, I
misunderstand
think,
that?
Climate models generally show the precipitation projections to be fairly flat, but in the decadal prediction, there was the ensemble mean was showing wet and warm also.
So do you know what was the cause for the increase in the precipitation in California? Because in the models, no.
Yeah, I haven't looked into that. No.
Yeah. Okay.
Okay, that concludes our oral sessions for today. So next is posters. Boom.